of Examsnet. Welcome to the question series of Examsnet. Students, you must have explored our website www.examsnet.com. This site is a great place for you to practice your entrance exam question papers because all the papers along with the detailed PDF solutions are available there. You also may download our app. The link is available in the description box for a better preparation of your exams. So students, today we'll be solving CBSE Class 12 Delhi Set 1 paper for physics. Maths and chemistry have already been uploaded for the same. Do explore that as well. So let's start with the very first question of the physics. Here we go. Best of luck. It says electric dipole of length 2 centimeter is placed at an angle of 30 degree with the electric field given by this. If the dipole experiences a torque of this much, the magnitude of either charge of the dipole is. All right, let's write down. First of all, you are having the angle, let's say theta, this is 30 degree. You are having E as electric field as 2 into 10 raised to power 5 newtons per coulomb. Then you are having the torque as 8 into 10 power minus 3 Newton meters. You are having the dipole of length 2 meters, 2 centimeters. That means 2A is equal to 2 or A is equal to, 2A, let it be 2A only. So 2A is equal to 0.02. This was centimeters. All right. So now, what you have to find out is charge. We know that torque is equal to PE sine theta, and P is equal to charge into dipole length multiplied by E sine theta. See, P is equal to Q into 2A. This is the formula. So what is Q? I don't know. I have to find that out. And 2A is 0.02. E is given to me as E is 2 into 10 power minus, not minus, 2 into 10 power 5 and the sine 30 degree. Torque is given to me 8 into 10 power minus 3. So these are the values which are given to me. Let's write it down. 10 into 10, 8 into 10 power minus 3 divided by 0.02 into 2 into 10 power 5. Sine theta is given by, okay, let's write sine theta. Right. So this is your charge. This is 8 into 10 power minus 3 into 100 upon sine theta is equal to 1 by 2. This will go over here, 1 by 2. Then you have 2 into 10 power 5. Right. And then this will cancel at 4. This cancellations. So this will cancel this. Q comes out to be 4 into 10 power minus 6. Yeah. So do 4 into 10 power minus 6. This is 4 coulombs or 4 microcoulomb. That's the right answer. Option E. This is the right answer to the question. Hope you got that. Next is question number 2. Two long parallel wires kept 2 meters apart away carry 3 ampere current each in the same direction. If the force per unit length on one wire due to another is. So you are having in the question 2 long parallel wires which are 2 meters apart. They are carrying 3 ampere current each. So in the question, you have I1 is equal to I2 is equal to 3 amperes and the distance is 2 meters. Current is flowing in the same direction. Current is flowing in the same direction. So you have F upon L is equal to mu naught I1 I2 upon 2 pi D. Right? You have to find out the force per unit length, right? This is force per unit length. So let's fill in the values. Mu naught is 4 pi into 10 power minus 7. 3 into 3, value for the two currents. 2 pi, D is 2. So this cancels and you have 9 into 10 power minus 7 newtons per meter or force upon length. This is equal to this. Since the currents, they are in the same direction, so the force will be attractive. Remember that. Correct answer is not given in the options above. Over here. Okay, okay. Yes, this is the one. Option D. This is the right answer. Hope you are clear with this, right? Next is question number 3. Which of the following has its permeability less than that of the free space? Copper, aluminium, copper chloride, or nickel? For the diamagnetic substance, which of the following has a permeability less than that of the free space? See, for the diamagnetic substance, susceptibility is negative. So permeability will be less than the of permeability will be less than permeability of for the free space. So aluminium has a relative conductivity higher than 1. If I talk about aluminium, it has a relative conductivity higher than 1. The formula is given by E is equal to B upon H. This is used to determine the magnetic permeability of aluminium, where B is your magnetic flux and H is the magnetizing force. Magnetic flux, and this is magnetizing force. Therefore, aluminium is having permeability less than that of the free space. So, B option. This is the right answer to the question. Hope you got that. Next is question number 4. A square-shaped coil of side 10 centimeter having 100 turns is placed perpendicular to a magnetic field which is increasing at 1 T per second. The induced EMF in the coil is. So you are having the number of turns as 100 and the side of square is 10 centimeters, which is equal to 0.1 meters. Rate of change of magnetic field is given by dB upon dt. This is given to you as 1 T per second. So EMF of the coil is NAD phi upon dt. Number of turns 100. A is equal to okay. A is equal A is area, right? Okay, fine. This is side. So side into side. And this is given to you as 1. So let's solve this. You will have this as 1 only. 1 volt induced EMF will be equal to 1 volt. That makes option D to be the right answer. Hope you got that. Next is question number 5. Which of the following electromagnetic radiation has the least wavelength? Gamma rays, visible rays, microwaves, or X-rays? The right answer to the question is gamma rays. The distribution of electromagnetic radiation according to the energy is known as electromagnetic spectrum. It's typically divided into 7 categories. They are gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, and radio waves. These regions are listed in the order of increasing wavelength and decreasing energy and frequency. Whereas gamma rays have the highest frequency, they are most energetic. And shortest wavelength among the major, shortest wavelength. Among the major form of the electromagnetic radiation, radio waves have the lowest frequencies, least energetic, least frequency, least energetic, and longest wavelengths. Hence, gamma rays have the this smallest wavelength. This is what we were asked about. A option is the right answer. Hope you got that. Next is question number 6. In a Young's double slit experiment, the screen is moved away from the plane of the slits. What will be the effect on the following? Angular separation of the fringes or the fringe width? First part of the question, angular separation of the fringes. See, the first thing, this remains, wait, this one remains constant. First one, angular separation remains constant and the fringe width increases. Now, why is that? When the screen is moved away, D, let's say screen is moved away, so D increases, distance increases, right? And you know beta is equal to lambda D upon small d. This D increases when the distance increases. Your beta, which is your fringe width, it also increases. And the angular separation, which is given by angular separation, which is given by lambda upon small d, it remains the same. Now, is it clear? So you have option C as the answer. 1 remains constant, whereas 2 increases. So option C is the right answer. Next is question number 7. The energy of the photon of wavelength lambda is which of these options? Energy of the photon of wavelength lambda, this is given by h c upon lambda. This is C, energy of the photon, actually this is given by h into mu. This is Planck's constant and mu is your frequency. And this frequency is frequency is equal to c upon lambda, or you have E is equal to h c upon lambda. This is the right answer, and you have option B as the correct option. Hope you got that. Next is question number 8. The ratio of the nuclear densities of two nuclei having the mass 64 and 125 is which of these? So you have a ratio of nuclear densities of two nuclei having these masses. So you are having first area, sorry, not A1 is equal to 64, and let's say A2 is equal to 125. You have R is equal to R naught A power 1 by 3. Density is given by atomic mass upon volume. So atomic mass, here I'm taking A as atomic mass. This is for the first one, and question number 8, the ratio of the nuclear densities of the two nuclei having the mass numbers this and this is which of these? Let's say the first mass number 64 and the second mass number 125. You are having R is given by R naught into A raised to power 1 by 3. Density is known as atomic mass upon volume. So this is equal to 4 by 4, A upon 4 by 3 pi r cube. This is A upon, let's write it properly, 4 by 3 pi r cube. This is equal to A upon 4 by 3 pi. R is given by R naught A power 1 by 3 power 3. Or this is equal to A upon 4 by 3 pi R naught cube A. A and A will cancel. This is your density, right? So now let's check with the options. No, what we had to find out is ratio of the nuclear densities. So that means you have to required ratio is rho 1 upon rho 2. This is 4 by 3 pi r naught 3 upon 4 by 3 pi r naught cube. So this is equal to 1 because this is independent of the mass. This is independent of the mass number. So this ratio is 1. We have D option as the correct answer. Hope you got that. Question number 9. During the formation of p-n junction, diffusion current keeps increasing. Drift current remains constant. Both diffusion current and drift current remain constant, or diffusion current remains almost constant, but drift current increases till both currents become equal. The right answer is that during the formation of a p-n junction, diffusion current remains almost constant, but drift current increases till both the currents are equal. This is the right answer, D option. Hope you understood this. Next is the question number 10. The diagram shows four energy levels of an electron in Bohr model of hydrogen atom. Identify the transition in which the emitted photon will have the highest energy. So these are the four energy levels. The right answer to the question, it is having the highest energy at the first level. The energy diagram is made using the proper scale to show the various levels. The transition state from 3 to 1 has the biggest energy difference. Has biggest energy difference. The first jump would be the one that releases the most energy and emits a photon with the maximum energy. Question number 10, the diagram shows four energy levels of an electron in Bohr model of hydrogen atom. You have to identify the transition in which the emitted photon will have the highest energy. So this is the first, second, third, and fourth level, and these are the jumps. This is the first jump, this is the second, third, and the fourth jump. Looking at these jumps, the transition from third state to the first state has the biggest energy difference. This is the biggest energy difference. The first jump would be the one that releases the most energy and emits a photon with the maximum energy. So this is the one, this option A, because this is the one which is emitting the most energy. You can easily see it from the figure itself. Hope you got that. Now let's move to the next question, number 11. Which of the following graphs correctly represents the variation of a particle momentum with its associated de Broglie's wavelength? So these are the four options given. De Broglie's wavelength is the wavelength that is connected to an object in relation to the momentum and mass. Typically, force of particle is inversely proportional to the de Broglie's wavelength. So a photon's momentum is determined by P is equal to E upon C, and this is equal to H upon lambda. Here E is the energy of photon, C is the speed of light in vacuum, H is the Planck's constant, and lambda is your de Broglie's wavelength. So according to de Broglie's, according to de Broglie, P is equal to H upon lambda, or this is momentum is inversely proportional to the wavelength. By this relation, we can conclude that the linear momentum of a photon is inversely proportional to the de Broglie's wavelength. The graph of P versus lambda should be a rectangular hyperbola. So which one is this? This is D option. This is your rectangular option, hyperbola. This is option D. This is the right answer to the question. Hope you are clear with this. Let's move to the next question, number 12. The capacitors, each of capacity 4 microfarad, are to be connected in such a way that the effective capacitance of the combination is 6 microfarad. This can be achieved by connecting which of the following? All three in parallel, all three in series, two of them in series, the combination in parallel to the third, two of them in parallel, the combination of that to the series with the third. Okay, before coming to the answer, let's discuss the question. See, when the capacitors are connected in parallel and series, the net capacitance are given by something like this. First of all, when the capacitors are connected in parallel, so equivalent capacitance is given by C1 plus C2 plus C3. And when they are connected in series, and this one is for parallel connection, 1 upon C equivalent is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. Here in the question, you have all the three capacitors equal to 4 microfarad. So C equivalent will be given by 1 upon 4, 1 upon 4, 1 upon C equivalent is equal to this much. So this will be no, I'll take this one, 6 microfarad. Wait, you are given the total equivalent reactance capacitance. This is equal to 6 microfarad. This is given to you. So now I want to have, these are the three capacitors given, and you want to have the equivalent capacitance of 6 microfarad. You can get it only if the two connected, first they are connected in series, and then that one is connected the third with the third one in parallel, like this. First two capacitors in series, and the third one in parallel. Okay, let's see. So C1 plus, first of all, series. So 1 upon C, let's say that CS is equal to 1 upon C1 plus this, 1 upon 4, 1 upon 4. This is 1 upon 2, or CS will be equal to 2. And you have C3 as a 4. So the C equivalent will be equal to CS plus C3, which is equal to 6 microfarad. So this is the right one. Okay, that means first two in series, and the answer, the resultant will be in the connection in parallel with the third. This is third option, option C. Hope you're clear with this. Let's move to the next question then. Question number 13. Which of the following statements about the series LCR circuit connected to an AC source is correct? It says if the frequency of the source is increased, the impedance of the circuit first decreases and then increases. If the net reactance XL minus XC of the circuit becomes equal to its resistance, then the current leads the voltage by 45 degrees. Third one, at resonance, voltage drop across the inductor is more than that across the capacitor. Fourth, at resonance, the voltage drop across the capacitor is more than that across the inductor. Okay. See, if the net reactance, that is XL minus XC of a circuit, becomes equal to the resistance, then the current leads to the voltage by 45 degrees. This is the right answer. Let's go for the explanation. For a LCR circuit, you have tan phi is equal to XL minus XC upon R. Or here you're having, in this particular, tan 45 is equal to 1. If I'm taking phi as 45, this is 1. So XL minus XC upon R, or you have R is equal to XL minus XC. So question number 13, which of the following statements about a series of LCR circuit connected to an AC source is correct? If the frequency of the source is increased, the impedance of the circuit first decreases and then increases. If the net reactance XL minus XC of a circuit becomes equal to its resistance, then the current leads the voltage by 45 degrees. At resonance, number 3, at resonance, the voltage drop across the inductor is more than that across the capacitor. Or number 4, at resonance, the voltage drop across the capacitor is more than that of the inductor. So if we talk about the right answer to the question is option B. If the net reactance XL minus XC of the circuit becomes equal to the resistance, then the current leads the voltage by 45 degrees. See, let's try to understand like why is the B option the right answer. For an LCR circuit, for LCR circuit, tan of phi, that is the angle, is equal to XL minus XC upon R. So tangent of, if I put theta is equal to, phi is equal to, no, let's see this from here only. So tangent phi is equal to, if I take that XL minus XC of the circuit becomes equal to resistance, if XL minus XC is equal to resistance, then this expression will be equal to R upon R, or this will be equal to 1, or this will be equal to tan 45. So this means phi is equal to 45, which is true in the case of B, right? If I'm taking the net reactance equal to the resistance, then I get the angle is equal to 45. So this clarifies that B is the right option. Hope you understood this. Next is, let's write it down. Option B. Next is question number 14. According to the Huygens principle, the amplitude of the secondary wavelets is equal in both the forward and the backward direction, maximum in the forward direction and zero in the backward direction, large in forward direction and small in the backward direction, or small in the forward and large in the backward direction. The right answer to the question, before that I'm telling you that, let's discuss the question. According to the Huygens principle, each point on the wavefront act as a source of secondary wavelets. And the amplitude of the secondary wavelets is proportional to the amplitude of the original wavelets. Amplitude of secondary wavelets. This is equal to the amplitude of the original wavefront. However, the amplitude of the secondary wavelets is same in all the directions. Option B is not correct. As it says, the amplitude of the secondary wavelets is not zero in the backward direction. Then the amplitude of the secondary wavelets relies on the geometry and the shape of the wavefront and may not be same in all the directions. Therefore, C and D are not necessarily true. So none of them is the exact answer for this, but A could be the correct in either either of the times. So equal in both forward and the backward direction. This is the right answer to the question. Hope you understood. Next is question number 15. The radius of the nth orbit in the Bohr model of hydrogen atom is proportional to. Okay. See, the radius of the nth orbit is given by radius of nth orbit is given by, let's say, Rn. This is given by 0.53 into n square upon z Armstrong. So that means it is directly proportional to n square, that is the orbit square. So we have first option as the right answer. Hope you understood. Next is question number 16. The resistance of an intrinsic semiconductor decreases with increase in its temperature. The reason says the number of conduction electrons as well as the hole increase in an intrinsic semiconductor with rise in its temperature. See, the assertion is true, but the reason is not. In an intrinsic semiconductor, the number of conduction electron and the holes is equal at the room temperature. However, the number of charge carriers, electrons and holes, charge carriers, increases with increase in temperature due to the generation of electron-hole pairs. This effect is more pronounced in higher temperature ranges. The increase in number of charge carriers lead to the increase in conductivity. This leads to increase in conductivity of the intrinsic semiconductor. Therefore, the resistance of this intrinsic semiconductor decreases with, therefore, resistance, because the conductivity is increasing, resistance of an intrinsic semiconductor decreases with increase in temperature. Decreases with increase in the temperature. This phenomena is known as intrinsic conduction. However, the reason is false. The reason, it says The number of conduction electrons as well as the hole increase in an intrinsic semiconductor with rise in its temperature. This is false because the increase in number of change carriers does not necessarily means increase in both electrons and holes. In fact, the number of electrons and holes may increase or decrease depending on the material and the temperature range. So assertion is correct, but reason is wrong. That makes the option to be the correct one. Hope you understood. Next is question number 17. The equivalent resistance between the A and B points is 2R. Okay, this is assertion and the reason says all the resistors are connected in parallel. Okay, let's see this before answering. See, in the given circuit, the resistors are connected in both series and parallel configurations. To calculate the equivalent resistance between the points A and B, we need to simplify the circuit using appropriate rules. If we apply the series and the parallel rules to the resistors, we can reduce the circuit to a single equivalent resistor between A and B point. Okay, so now in the question, you are given that equivalent resistance, this is equal to 2R. So this is right, that this may be correct if I say this. Now let's discuss how you get this to R like. What happens is you are having this point A. This is point A. Let this point be X. This point be Y, and this point be some um, G and H. Okay, fine. So now from here you are having A and G. Point is here, and you are having the point. This is from A to G. You are having the resistance. Question number 70, the equivalent assertion says the equivalent resistance between the 2 points A and B in the given network is 2R. And the reason says all the resistors are connected in parallel. You have to check which is the right answer. See, the given circuit has resistors which are connected both in series and in parallel. To calculate the equivalent resistance between the 2 points, we need to simplify the circuit using appropriate rules. If we apply the series and the parallel rules to the given resistors, we can reduce the circuit to a single equivalent resistor between the 2 points. And that is equal to 2R according to the assertion. Let's check if this is the point A and this is the point B. This is point A. And here you have the point B. So from A you start, and this is 2 ohm resistor. From here it goes, let's say this is the point some H. So this is the point, or let's say that is the point X. Okay, let it be H. So this is the point H, and then from A, and this is the point I. From A, you are having a 2 ohm resistor over here, 2 ohm resistor over here. This is I point, and from I to H, you are having a 2 ohm resistor also over here. From H to B, again a 2 ohm resistor, 2 ohm resistor. From here to here, you are also having a 2 ohm resistor. See, now what happens? This 2 over 2 is equal to 1, and this 2 over 2 is equal to 1. Since they are equal values, so the middle resistor, this can be neglected. Now the equivalent resistance will be given by, this is the point A, this is the point B, this is the point H, this is the point I. So this is like this. This is the point B and this. So each is 2 ohms. Right. So now the equivalent resistance, see, these two are connected in parallel. This one and this resistor, they are connected in parallel. Similarly, this and this resistor are connected in, sorry, not in parallel, they are connected in series. So this two are connected in series, and you know the equivalent resistance for the series is given by 1/2 plus 1/2, like 1 by, let's say R1 is equal to 1/2 plus 1/2. This is equal to 1. And yes, and similarly 1 by R2 for these two resistance, this is given as 1 by 2 plus 1 by 2. This is equal to 1. So you have R2 as 1 and R1 as 1. So the equivalent resistance for this is equal to 1. Similarly, the equivalent resistance for this much portion is equal to 1. So now they are connected in parallel. Like if I say this is R1 and this is R2, they are connected in parallel. And now the net resistance will be given by R1 plus R2, which is equal to 2. Right. So that's it. You have 2R as a net resistance. 2R or whatever, like 2 ohm. Actually, this was equal to 2R. So 2R will be the net resistance. Now, the reason says all the resistors are connected in parallel. No, we just saw that these resistors are connected in series. So assertion is true, but the reason is false. So that means you have C option as the correct answer. Hope you understood this. Next is question number 18. Assertion and reasoning question again. The deflection torque acting on a current carrying loop is 0 when its plane is perpendicular to the direction of the magnetic field. The reason says the deflecting torque acting on a loop of magnetic moment M in a magnetic field B is given by the dot product of M and B. In this question again, the assertion is true, but the reason is false. The deflecting torque acting on a current carrying loop placed in a magnetic field is given by this. T is equal to cross product of M and B, where T is a deflecting torque. Tau actually. Tau is your deflecting torque. And then you have M is your magnetic field. And B is, sorry, M is your magnetic, what did I say? M is your magnetic moment. And B is magnetic field. The cross reply denotes that it's a vector product. Now, the angle between the magnetic moment vector and the magnetic field is 90° when the plane of the loop is perpendicular direction of the magnetic field. At this situation, both the deflecting torque and the vector product of the two vectors reach their maximum values. The two vectors dot product, however, is 0. Okay, so that means assertion is correct, but reason is false. So C is the right answer. Hope you understood this. Next is question number 19. You have to draw a graph showing the variation of potential energy of a pair of nucleons on as a function of their separation. Indicate the region in which the nuclear force is attractive and is repulsive. Graph showing the variation of potential energy between a pair of nucleons as a function of their separation is something like this. The graph. At a distance of point like 0.08 FM, the potential energy is at its lowest level. This is the potential energy, and then this is at its lowest level. The nuclear force is appealing for distances greater than R0 from here, this side. The two objects are distant from one another by less than R0. Nuclear forces are repulsive, as you can see it from here, else they are attractive. At R is equal to 0, this is the equilibrium position. Nuclear force readily diminishes over here. So this is the right graph. And if you also see, this is the one. Here the potential energy is at its lowest. This is the area of repulsion, attraction, and separation. Hope you understood this. Let's move to the next question. Question number 20. How will the de Broglie wavelength associated with an electron be affected when the velocity of the electron decreases and the accelerating potential is increased? You have to justify your answer. This is a choice question, or you can attempt this one. Let's go with the first one. A part. A question, first part says you, how will the de Broglie's wavelength associated with the electron be affected when the velocity of the electron decreases? See, the de Broglie's wavelength formula states that the wavelength is inversely proportional to the electron momentum. Momentum is the result of mass and velocity. So when the electron velocity decreases, momentum also decreases. Right. As a result, de Broglie's wavelength will increase because this is inversely proportional. This will increase. As the velocity of the electron decreases, wavelength will increase. This is your first part. A question, first part. Second one, accelerating potential is increased. You have to justify your answer. See, as the accelerating potential is raised, the electron speed rises as well. The electron's momentum, if the speed is rising, momentum is also rising. This is the second part. If the speed is increasing, first of all, if the acceleration potential is increased, so this is increased, that means speed is increased, that means momentum is increased. So according to the de Broglie's wavelength, the wavelength will decrease because this is inversely proportional to the this momentum. Wavelength is inversely proportional to wavelength. So if the momentum is increasing, wavelength will decrease. That's it. This is your A part. So what will happen to the wavelength? It will decrease in this case, and it will increase wavelength I'm talking about. Okay. Now, the choice question B part. How would the stopping potential for the given photosensitive surface change if the frequency of the incident radiation were increased? If the frequency of the incident radiation is raised, the stopping potential for the specific photosensitive surface would rise. This is due to the fact that according to the photoelectric equation, the stopping potential is directly proportional. Stopping potential is directly proportional to the frequency of incident radiation. That is, K max is equal to HF minus pi, where H is Planck's constant, F is frequency of the incident radiation, and pi is the rate. Work function of metal. Okay, now K maximum is your maximum kinetic energy of photoelectrons. Hence, the input radiation frequency rises. So does the stopping potential energy needed to halt the photoelectrons, while the kinetic energy of the photoelectrons that are emitted will decrease. Hope you understood this. Now, the second part, the intensity of the incident radiation were decreased. See, the decrease in the intensity of the incident radiation would have no impact on the stopping potential for a specific photosensitive surface, because stopping potential is solely dependent on the frequency and not on the intensity. Stopping potential is solely dependent on frequency only and not on intensity of the incident radiation. The frequency of the incident radiation alone determines the photoelectron's kinetic energy, while the number of photoelectrons emitted for the surface is inversely proportional to number of photoelectrons emitted from the surface is inversely proportional to the intensity of received radiation. Hence, lowering the incident radiation's intensity would result in fewer photons being released, but it would have no effect on the kinetic energy or the stopping energy. Hope you understood that. Next is question number 21. Identify the electromagnetic wave whose wavelength range is from about 10 raised to power minus 12 meters to 10 raised to power minus 8 meters. Electromagnetic waves of wavelength range this much, 10 raised to power minus 2 meter to 10 raised to power minus 8 meter. Question number 21, identify the electromagnetic wave whose wavelength range is from about 10 raised to power minus 12 meters to 10 raised to power minus 8 meter. Electromagnetic waves of wavelength given by this range are known as X-rays. They are used as diagnostic tool in medicine, for tool in medicine, for scientific research, and crystallography. The second one, 10 raised to power minus 3 to 10 raised to power minus 1 meters. This one are the microwaves which are used in radar. They are microwaves. I'm sorry, my pen is lagging. So, okay. They are the microwaves which are used in radar and microwave telecommunication, microwave ovens, etc. Microwave telecommunications and ovens, etc. So this is the answer to the 21st question. Hope you are clear with this. Let's move to the next question now. It says depict the orientation of an electric dipole in a stable and unstable equilibrium in an external uniform electric field. Write the potential energy of the dipole in each case. Number one, it is says in the stable, when the dipole of an aligned parallel when the dipole is aligned parallel to the electric field, that is the angle between the dipole and the electric field is zero, then the dipole is in stable equilibrium. When dipole is aligned parallel to the electric field, that is angle between the dipole moment and electric field is zero, then the dipole is said to be in the stable equilibrium. And when the dipole is aligned anti-parallel, the same thing, it is aligned anti-parallel to the electric field, that is the angle between the dipole moment and the electric field is equal to 180 degree, and this is anti-parallel, then it is in the unstable equilibrium. Hope you are clear with this. Then let's move to the next question, number 23. Question number 22. Depict the orientation of the electric dipole in a stable and an unstable equilibrium in an external uniform electric field. Write the potential energy of the dipole in each case. See, when the dipole, you are having two cases. The first one is stable and the another one is unstable. When the dipole is aligned, when dipole is aligned parallel to the electric field, then it is stable. Then it is said to be stable. And for the unstable, when the dipole is aligned anti-parallel to the electric field, then it is said unstable. This is the first point. And the second point, angle between the dipole moment and the electric field is zero for the case of stable. Angle between dipole moment and electric field is zero, and for unstable, angle between dipole and electric moment is equal to 180 degree. Right. Hope we are clear with this. And now for the stable equilibrium, you have the theta is equal to 0 degree, and for the unstable, you have theta is equal to 180 degree. For the stable, the potential energy, because you are asking for the potential energy also. So stable, the potential energy is U is given by potential energy U is equal to minus PE cos of theta. So you have this as minus PE cos 0. Cos 0 is equal to 1. So this is equal to minus PE. U in the case of stable, and the potential energy in the case of unstable is given as U is equal to minus PE cos 180 degree. Cos 180 degree is equal to minus 1. So This will be equal to PE. Hope you are clear with this. Then let's move to the next question. Question number 23, write the expression for the Lorentz force on a particle of a charge q. Moving with the velocity v, magnetic field B, when is the magnitude of the force maximum? Show that no work is done by this force on the particle during its motion from R1 to R2 point. So let's pick up this one. Where is the magnitude of this force maximum? First thing, Lorentz force is equal to magnetic plus electric force. So force is equal to Q cross product of V and B vector. So this force is equal to Q V B sine of angle between them. Now its theta is 90 degree. When theta is equal to 90 degree, then Lorentz force is maximum. If ds is the instantaneous displacement, is instantaneous displacement of the charge, and is also perpendicular to F, then work will be equal to the dot product of F and ds. So this will be equal to F S cos of angle between them. So this is Fs theta is equal to 90 degree. That is equal to 0. So work done is equal to 0. Hence, no work is done by this force on a particle during its motion from R1 to R2 point. This is proved over here. Okay. Now, when is the Lorentz force maximum? We also discussed its maximum when theta is equal to 90 degree. All right. So now the B part, or this is a choice question. You have to solve this part also. It says let's clear the screen. A long straight wire AB carries a current I. A particle mass M charge Q moves with velocity V parallel to the wire at a distance D. From it is as shown in the figure. Obtain the expression for the force experienced by the particle. Mention its directions. All right. Magnetic field induction at P due to the current I in a long wire is given by, see if I'm looking at this. So magnetic field, I'm repeating, at the point P, if this is the particle, like let this be the point P. So magnetic field at the point P due to the current I in the long wire AB is given by this AB wire. This is given by mu naught to I upon 4 pi into D. It acts perpendicular to the plane of the paper inward, represented by it act perpendicular to the plane of the paper inward, represented by n cap. So Lorentz force acting on force acting on particle P can be given by F is equal to Q V cross B, or this is equal to E. The charge is E, V, and B is given by mu naught into 2I upon 4 pi D multiply N factor. Because we are talking about the vector form. So F is equal to mu naught I E V upon 2 pi D V vector cross N vector. So the force, normally force is equal to mu naught I EV upon 2 pi D, acting in the plane of the paper away from the wire. Acting in the plane of the paper away from the wire. Hope we understood this. Next is question number 24. The potential difference applied across a given conductor is doubled. How will this affect the mobility of the electrons, the current density of the conductor? First part. So, how will it, the potential difference is applied, it's doubled. How will it affect the mobility of the electron? See, mobility of the, this is the first part, mobility of electrons. Sorry. Mobility of the electrons is given by Vd upon E. Mm. Question number 24. The potential difference applied across a given conductor is doubled. How will this affect the mobility of the electrons? Number 2. The current density in the conductor. See, the mobility of the electrons is given by E upon V of Vd, that is the drift velocity upon E. Drift Vd, where this is your mobility of electrons. Vd is your drift velocity and E is your electric field density. So also one more thing, that E is equal to V, that is the potential difference upon L. So this mobility upon of the electrons is given by Vd upon V into L. So that means it is inversely, the mobility of the electrons is inversely proportional to the potential difference. So mobility of the electrons, if it is the potential difference is double, the mobility of the electrons will decrease. Now the second, the current density in the conductor. One thing, if V is doubled, mobility will be halved. Now the second part, it's talking about the current density. This is given by NE, drift velocity. So this is equal to N into drift velocity is given by this, or this is equal to NE square V tau M into L. So that means current intensity is directly proportional to the this potential difference. Now, if that means if this becomes double, this also becomes, current density also becomes double. That's it. So hope you're clear with this. Next is question number 25. Two coils C1 and C2 are placed close to each other. The magnetic flux phi2 linked with the coil C2 varies with the current I1 flowing in the coil C1 as shown in the figure. So from the figure, you have to tell, number one, the mutual inductance of the arrangement. Let's go for this first. So you are having phi2. This is the magnetic flux of C2 coil. I1 current in C1. Let the number of turns in C1 is equal to N1 and in C2 is equal to N2 according to Faraday's law. This is d phi, mutual inductance is equal to d phi upon dt, or this is E21 is equal to minus N2 d phi upon dt. This is equal to minus N2. So d phi is vector this on dt. That means N2 phi 2 is directly proportional to I1 and N2 phi 2 is equal to M21 I1. M21 is your mutual inductance. So this is equal to M21 is equal to N2 phi 2 upon I1. That's it. Now the second one, you have the rate of change of current that will induce an EMF of 100 volt in the coil C2. Okay, so induced EMF, this is the second part. Induced EMF is given by E is equal to minus L d upon I upon dt or di upon dt is equal to minus E upon L. So di1 upon dt, this is equal to minus 100, 1 upon L. L is the inductance of the, here, L is inductance of C2. Hope you are clear with this. Next is question number 26. Now we are moving to section C. Here will be some 3-number questions. Now this is a choice question, or is there. So first question, a plane wave front propagating in a medium with refractive index mu1 is incident on a plane surface making an angle of incidence I. It enters into a medium of refractive index mu2. You have mu2 greater than mu1. That means the refractive index of the second surface is greater than the first surface. Using Huygens construction of secondary wavelets to trace the refracted wave front, hence verify Snell's law of refraction. Question number 26, section C, A and B parts. You have a choice over here. A part says a plane wavefront propagating in a medium with the refractive index mu1 is incident on a plane surface, making an angle of incidence I. It enters the medium of refractive index mu2, where the second medium is having a higher refractive index than the first one. Using Huygens construction of secondary wavelets to trace the refracted wavefront, hence you have to verify the Snell's law of refraction as well. All right, to understand the problem, let's see this figure. So here you have a plane wavefront AC, which is incident on the plane of separation, that is your XY. Over here. Now, this is the this is a medium with the refractive index mu1, mu2. Mu2 is greater than mu1. This is making an angle of I, and this is your angle of incidence. When the wavefront touches the XY plane at the point A becomes the source of secondary wavelengths. Thus, the whole waveform passes through XY only, right? And each point on the AF becomes a source of the secondary wavelengths. Now, when the point C of the wavefront in medium 1 traverses CF by a distance of CF by a distance in the time t, the wavelet from the point A transverses through AD in that case. If V1 and V2 are the speeds of light in medium 1 and V2 is the speed of the light in medium 2 respectively, then AD will be given by V2t and CF will be given by V1t. So refractive wavefront DF over here, this DF over here, which is obtained by drawing a tangent to the arc shown over here. So this refractive wavefront DF, which is obtained by drawing a tangent to this arc having the radius, this is V2D, and the center as A. The angle made by the tangent with the plane XY is this R. This is your angle of refraction. The perpendiculars drawn from the wavefront AC. This perpendicular drawn from the wavefront AC are the incident rays, and the perpendicular drawn from DF are refracted rays. AN, this AN over here, this is AN and TF, they are the perpendiculars drawn on XY, the plane of separation of the two media. So therefore, now you have this angle CAF as angle of incidence, which is nothing but 90 degree minus angle NAC. Look over here. So this CAF is nothing but the angle 90 degree minus angle NAC. This one, NAC. Right? Because they both are making a 90 degree angle. So this is equal to 90 minus NAC is equal to 90 minus angle SAN, and your angle SAN was your angle of incidence. All right. So similarly, you have one more angle QFT is equal to angle R, and in the triangle ACF, you have sine I is equal to CF upon AF. Please refer to this figure. You can take a screenshot of it. So sine I is equal to CF upon AF, which is equal to V1T upon AF. Similarly, in the triangle ADF, you have sine R is equal to AD upon AF, which is equal to V2D upon AF. Let's divide both of these equations. You have sine I upon sine R is equal to, this is V1T upon V2T. So this will be V1 upon V2. This is a refractive index of 2 with respect to 1, and this verifies your Snell's law. This verify Snell's law. Hope you are clear with this. Let's move to the next question then. Students, here I would like to clarify once more that mu refractive index is equal to C upon V. So if I'm taking for the velocities V and V1 and V2, this will be mu1 is equal to C upon V1 and mu2 is equal to C upon V2. Let's see. From here you will have V1 is equal to C upon mu1, and from here you will have V2 is equal to C upon mu2. So this will become now sine I upon sine R is equal to C upon mu1 upon C upon mu2. So this will be equal to mu2 upon mu1. That means mu1 sine I is equal to mu2 sine R. I hope this is absolutely clear. Okay, now the second part. Now, it says using Huygens construction, you have to show a plane wave is reflected on from a surface. You have to verify, hence verify the laws of reflection. Now, if we are talking about the laws of reflection, there are two laws of reflection. First one says that angle of incidence is equal to angle of reflection. Second says incident ray, reflected ray, normal, or at the point of incident all lie in the same plane. So these are the two laws of reflection. Using the Huygens construction, I have drawn this. This is the Huygens construction. Here, AB is your this incident wavelength, and your CD is the reflected wavelength. Now, for the first law of reflection, let's say XY be the plane reflecting surface. AB be your plane wavefront, incident on the circuit on the surface as shown over here. So now using Huygens principle, every point on the wavefront AB is a source of secondary wavelet, and the time during which the wavelet reaches C, the reflected wavelet from A would arrive at D. Right. So therefore you have a T is equal to BC upon V, or this is equal to AD upon V. That means BC is equal to AD. Let's say this is 1. Here V is your velocity of light in the given medium. Now in the triangle ABC, in the right angle triangle ABC, you have sine I. This is equal to BC upon AC, or BC is equal to AC into sine I. Let's say this is 2, and okay, that was 1. Okay. Now in the triangle ADC, you have sine R as AD upon AC, or AD is equal to AC into sine R. Let's say this is equation 3. Now putting 2 and 3 in equation 1. Put 2 and 3 in equation 1. You will get AC into sine I is equal to AC into sine R. That gives you sine I is equal to sine R, or you have angle I is equal to R. This is your first law of reflection, right? Now the second law. From the figure, we find that the incident ray, reflected ray, and see the incident ray, reflected ray, and the normal, they all are lying in the same plane. So this is your second law of reflection. We'll get clear with this. So let's move to the next question then. Question number 27. Alternating voltage of 200 volt, 220 volt is applied across a device X. Current of 0.22 amperes flow in the circuit, and it lags behind the applied voltage in the phase by pi by 2 radian. When the same voltage is applied across another device Y, the current in the circuit remains the same, and it is in the phase with the applied voltage. Fine. You have to tell the X and Y. Also calculate the current flowing in the circuit when the same voltage is applied across the series combination of X and Y. Now for the X and Y, since the current behind the, for the first one, since current lags behind the voltage, so what is X? It's an inductor. And the second one, in the for the Y, current and voltage, they be in the same phase. In same phase, that makes Y a resistor. Okay, now you have to calculate the current flowing in the circuit when the same voltage is applied across a series combination of X and Y. When you're having a series combination of this inductor and the resistor, this is the second part. So what you had to find out was the current flowing. Okay, for that, let's find out first of all XL, that is, you have voltage upon current. So voltage is 220, current is 0.22. This is equal to 1000 ohms. So you have the resistance also. The resistance, this is equal to 1000 ohms. You know the impedance Z is given by R square plus XL square. So this is equal to 1000 square plus 1000 square. This will be equal to 1000 root 2 ohm. So the required current will be, when both are connected in series, so required current will be equal to 220 upon the Z, which is equal to 1000 root 2. This will cancel, and like after doing all the calculations, you will have 0.155 ampere. So this is the answer to the question, 0.155 ampere. Hope you're clear with this. Let's move to the next question then. Question number 28, state the basic principle behind the working of an AC generator. Briefly describe its working and obtain an expression for the instantaneous value of EMF induced. Fine. See, your AC generator works on the principle of the Faraday's law of electromagnetic induction. Electromagnetic induction. Whenever a coil is rotated in a uniform magnetic field about an axis perpendicular to the field, the magnetic flux linked with the coil changes and an induced EMF is set up across the ends. So this is the basic principle behind the working. Let's talking about the working of the AC generator. Question number 28, state the basic principle behind the working of an AC generator. Briefly describe its working and obtain an expression for the instantaneous value of the EMF induced. AC generator works on the basic principle of Faraday's law of electromagnetic induction. Whenever a coil is rotated in a uniform magnetic field, an axis perpendicular, whenever a coil is rotated in a uniform magnetic field about an axis perpendicular to the field, the magnetic flux linked to the coil changes. And an induced EMF is set up. Induced EMF is set up across its ends. Right. Now the working of an AC generator, second part. When the armature rotates between the poles of the magnet upon the axis perpendicular to the magnetic field, the flux which links the armature changes continuously. Due to this, an EMF is induced in the armature. This produces electric current through galvanometer and slip rings and brushes. The galvanometer swings between the positive and the negative values. This indicates that there is an AC current, alternating current, flowing through the galvanometer. All right, now let's talk about the EMF which is induced in the coil. For that, let's consider EMF induced. For that, let's consider a coil with M turns, A area, and rotated with omega angular velocity in a magnetic field with the B flux, magnetic flux. Um, its axis being perpendicular to the field, of course. This perpendicular to the field. Now, when the normal of the coil is an angle of theta to the field, the flux through the coil is, let's write down, when the normal to the coil is at an angle of theta to the field, the flux through the coil is equal to B A N cos theta. So this is cos B A N cos omega t. Theta is equal to omega t, since theta is equal to omega t. Hope you are clear till here. So induced EMF is minus d phi by dt, or this is equal to minus d B A N cos theta divided by dt. So this is equal to BAN. I'm changing the cos into sine. So this will be BAN omega sine omega t. The maximum value of the induced EMF, that is E naught, is when this omega t is equal to 0. Maximum value of EMF, that is your E naught, is when omega t is equal to 90 degree, because then your this will be equal to 1. Now this is when the coil is in the plane of the field, and this is given by E is equal to BAN omega. All right. So this is the expression. Hope you are clear with this. Let's move to the next question then. Question number 29. A part A part, briefly describe how the current sensitivity of a moving coil galvanometer can be increased. B, and there is also B. First of all, let's solve the first part. So you have to tell the sensitivity of a moving coil galvanometer, how that can be increased. See, the sensitivity of the moving coil galvanometer can be increased by increasing the number of turns, area of the coil. Let's write down. Sensitivity can be increased by increasing, number one, number of turns in the coil, increasing area of coil, and increasing magnetic field. Whereas by decreasing the couple per unit twist of the suspension. Decreasing couple per unit twist of the suspension. All right. So the second one, the galvanometer shows full scale deflection for the current IG. A resistance R1 is required to convert into voltmeter of range 0 to V, and the resistance R2 to convert into voltmeter of the range this. Find the resistance of the galvanometer. Okay, so this is something. See, this is a circuit for here's your voltmeter. This is your galvanometer. This is the point A. This is the point B. Down, down. Here is your V. This is IG flowing, and this is your voltmeter. Yeah, I think everything is made. All right. Now, in the first case, potential difference across A and B is V is equal to IG R1 plus IGR. This is your R. So Ig is equal to V upon R1 plus G, where G is the resistance of the galvanometer. G is resistance of the galvanometer. So R1 plus G is equal to V upon Ig. Or you have R1 is equal to V upon Ig minus G. G is equal to these two things, V upon Ig minus R1. So this is the first case. Now in the second case, you have Ig is equal to V upon R2 plus G. R2 is the resistance required to change the voltage. This is the second one. R2 is the resistance required to change the voltage from from this 0 to 2V, and R1 was from 0 to V. Okay. R2 resistance required to change range to 2V. So your in this case, because this has to be 2V, so 2V upon R2 plus G. So R2 plus G is 2V upon Ig, or R2 is equal to 2V upon Ig minus this. R is equal to 2V upon Ig minus R2. Okay, so yeah. So the resistance of the galvanometer for the first, this is for the second case. This is your second answer, and this one yours your first answer. Okay. So hope you're clear with this. So here was your G, because in the question it was asked the resistance of the galvanometer. This comes out to be that this is equal to G. Okay. So this is your first answer, and this one is your second answer. All right, let's move to the next question. Number 30, state the differentiate between the distance of the closest approach and the impact parameter. So again, a choice question. First question, two parts. B question, two parts. Let's go with the first one. It says you have to differentiate between the distance of closest approach and the impact parameter. So the term distance of closest approach describes the smallest distance that the two particles or object must maintain when interacting, such as when they collide. It's usually quantified in terms of physical distance, such as meters, this meters and centimeters, because this is where the particles are closest to one another. The beginning of the conditions of the interactions, such as particles' initial locations, velocities, forces, influence the distance of the closest approach. Whereas if I talk about the parameter approach, this on the other hand is a measurement of the separation between the particles trajectory and a target item such as nucleus during a collision. The perpendicular distance between the particle's original trajectory and the target object center is what is meant by this term. The impact parameter, which is crucial for understanding the collision's dynamics, is often referred in terms of the distance such as meters and millimeters. So this is the answer to the first question. The second one, determine the distance of the closest approach when a alpha particle of kinetic energy this much approaches a nucleus with the atomic number 79, stops and reverses its directions. Okay, let's say R be the center. Let R be the center to center distance between alpha particle when alpha particle is stopping. When alpha particle is at the stopping point. Then k is equal to 1 upon 4 pi E naught ZE into 2E upon R. So you are given here that k is equal to 3.95 MeV. So this becomes 3.95 into 10 power 6, right? Into E is 1.6 into 10 raised to power minus 19. This is joules. This is B. So this now the R will be equal to 1.4 E this 2ZE square upon K. So this is equal to 9 into 10 power 9 into 2 into 79 into 1.6 10 power minus 9 whole square divided by 3.95 into 10 power 6 into 1.6 into 10 power minus 19. On solving this whole thing, you will get your answer as 576 into 10 raised to power minus 16 meters, or this is equal to 5.76 into 10 raised to power minus 14 meters. This is the answer to the second part, 5.76 into 10 raised to power minus 14 meters. Hope you are clear with this. Now the second part, odd choice in the question. This is B part. It says you have to state three postulates of the Bohr's theory of hydrogen atom. The three main postulates that Niels Bohr gave to the Bohr's model of the hydrogen atom are the B part. First B question, first part. Atoms have a series of stable orbits which within electrons. Atoms have a series of orbits within which electrons will exist while not emitting any energy. Every orbit corresponds to a selected energy. Every orbit corresponds to selected energy. The second one, energy of the outer orbit is greater than the inner orbit. Energy of outer orbit is greater than energy of the inner orbit. When the electron jump from an orbit to another, there is an energy difference which is given by when electron jumps from one to one to another orbit. There's an energy difference which is given by n into h into v. The angular momentum of the electron, the third one, the angular momentum of the electron is quantized, which can be shown like this. Angular momentum is of electron is quantized. This is given by nh upon 2 pi, where n can be 1, 2, 3, 4, like that. All right, so this is the first part, the Bohr's model. The second one, determine the distance of the closest approach when an alpha part, oh, sorry, this is the B part. Find the angular momentum of an electron revolving in the second orbit in the Bohr's hydrogen atom. So let's go with this. Your B part second. Okay, we already have discussed that the angular momentum is given by this. So angular momentum of an electron revolving around the nucleus in the hydrogen atom is quantized, and this is given by L is equal to NH upon 2 pi. So here N is equal to 2. So this will be equal to 2 into H upon 2 into pi. This is equal to H upon pi. H is 6.6 into 10 raised to power minus 34 and with the pi. Okay, so this on solving will give you 2.10 into kg meter square per second. So this is the answer to the question. 2.10 kg meter square per second. Hope you're clear with this. Let's move to the next question. Question number 31. Again, there is a choice. A question, first part. Let's start from here. Explain how free electrons in a metal at constant temperature attain an average velocity under the action of an electric field, hence obtain the expression for it. All right. So we know that the free electrons are the current carriers in a metallic conductor, and these free electrons move randomly in all directions and constantly collide with the positive ions inside the metal, due to which the average thermal velocity equals to zero. Now, when the electric field is applied between the two ends of the metallic conductor, then the electric field is set up across the two ends of the conductor, and now free electron moves in the particular direction due to the external electric field, and they get accelerated. So let's derive the expression for the drift velocity. Expression for the drift velocity. When a potential difference is applied across the conductor, the electric field is produced and free electrons are electric field is produced and free electrons are acted upon by the electric force, which is given by minus AE. Now, due to this, electrons accelerate and keep colliding with each other and acquire a constant average velocity, let's say VD. So you have F is equal to minus EE, that is equal to E is given by V upon L into E. So you have E is equal to V upon L. As you know, acceleration is minus of force upon the mass. This is this. Also, we know that V is equal to U plus AT. So initially U is equal to 0. T is equal to your relaxation time. So VD is equal to minus A into relaxation time, or VD is equal to minus EV upon LM. I'm picking it up from here. So multiply T. This is the expression required one. Right now, the second part, considering two conducting wires A and B of the same diameter but of different materials joined in series across a battery. The number density of electrons in A is 1.5 times that in B. You have to find the ratio of the drift velocity of the electrons in wire A to that of wire B. Okay, so you have A question. Second part. In a series circuit, current flowing through the entire circuit is same. Series current through the entire circuit is same. So you have I is equal to NA, AEVD, A. This is both the current is equal. So this is NB, AE, VD for B. So VDA, let's divide both. They are equal, right? So I'm cancelling the equal terms like this, and this will cancel. So you have VDA upon VDB is equal to NB upon NA. And you are given that NA is equal to 1.5 NB. This is given in the question. Right. Number of electrons in A is equal to this much. So this becomes 1 upon this. This is equal to this, or this is 2 by 3. So that means VDA is to VDB is equal to 2:3. Right. This is what we needed to find out. We needed to find out that ratio. This is 2:3. Hope you're clear with this. So now let's move to the second question, second part, B part. A cell of EMF E, internal resistance R, is connected across a variable load resistance R. Draw the plots showing the variation of thermal terminal voltage V with R and the current and in the load. Okay, let's read it once again. EMF, the cell EMF E, internal resistance R is connected across a variable resistance, load resistance R. You have to draw the plots showing the variation of the terminal energy in R, current, and load. Okay, fine. So first of all, graph between the terminal voltage and the load resistance. B question, first part. Graph between this is given by, this is your R and V. This graph is something like this. Not like this, wait. This is like this, okay? Stable. So graph between terminal voltage and current, let's make graph between current, terminal voltage and current. So here is your I, here is your terminal voltage. This graph goes like this, right? Yeah. Next is the second part. Three cells, each of EMF E, internal resistance 2R, 3R, 6R, connected in parallel across a resistor R. Obtain expression for the current flowing through the circuit. Number one. Number two, terminal potential across the equivalent cell. All right. So this is the, they are connected in parallel. So this looks something like this. Here you have, these are resistance 2 ohm, 3 ohm, 6 ohm, and this is your resistance R. They are connected in parallel. Let's say this is A and this is B point. You have to find out RAB first. So this, since they are connected in parallel, so 1 upon RAB is equal to this. 1 upon 2R, this and this R. Yeah, this is R, right? 3R and 6R. So this will be equal to 1 upon R. I'm taking outside 6, 3 plus 2 plus 1. This is equal to 1 by R because this is 6 and 6. This will cancel. So R A B will be equal to R. This is equivalent internal resistance. So equivalent EMF of cells in parallel is given by E equivalent is equal to E1 upon R1, E2 upon R2, E3 upon R3 divided by 1 upon R1, R2, R3. So this is 2R, this is the 3R and 6R. This is equal to this. Okay. So now R and R, like, let's take the LCM first of all. This will be E. This can be written like this. So this is equal to E only. So that means the equivalent EMF of the cells in parallel is equal to E. Current flowing through the circuit is given by E equivalent divided by R plus RP. So this was E R plus small r. Potential drop across E is V is equal to I into R equivalent. So this is equal to small r into E upon R plus R. There's a potential drop across E, and this is your second answer. Yeah, this one. So potential drop is equal to R into E upon R plus R. All right. So this is the answer to the question. Under the current flowing through the circuit, this is given by this. Hope you're clear with this. Then let's move to the next question. Question number 32. Draw the circuit arrangement for studying VI characteristics of a PN junction diode in the forward biasing and reverse biasing. Draw the typical VI characters of a silicon diode. Describe briefly the following terms: minority carrier junction in forward biasing and breakdown voltage in the reverse biasing. Okay, let's move step by step. The circuit was showing the studying the VI characteristics of a diode are shown in these two figures A and B. For different values of the voltages and the value of the current is noted. A graph is plotted between C and I over here. This is in figure C. From the VI characteristics of a junction diode, it is very much clear that it allows current to pass only when it is forward biased. So for an alternating voltage is applied across a diode, the current flows only in the part of the cycle when the diode is forward biased. This property is used to rectify alternating voltages. Now let's see, you want to have a briefly describe the magnetic carrier injection in forward biasing. This is due to the applied voltage, electrons from the N side cross the depletion range and reach the P side when the minority where they are minority carriers. Similarly, holes from P side. Similarly, holes from P side cross this junction to reach the N side where they are the minority carriers. This process under the forward bias is known as minority carrier injection. So let's write it over here again. Due to the applied voltage, electrons from N side cross the depletion range to reach the P side where they are minority carriers. And similarly, holes from the P side cross the junction and reach the N side where they are the minority carriers. Hope you're clear with this. Second one, the breakdown voltage in reverse biasing. It is a critical reverse bias voltage at which the current is independent of the applied voltage. Breakdown voltage is critical reverse bias voltage at which current is independent of the applied voltage. Hope you're clear with this. Now let's move to the second part of the question, B part. Name two important processes involved in the formation of PN junction diode with the help of the circuit diagram. Explain the working of the junction diode as a full wave rectifier. Draw its input-output waveforms. State the characteristic property of the junction diode that makes it suitable for rectification. So in the PN junction, the processes of diffusion and drift, they are crucial. Majority carriers diffuse into high concentration. A majority carriers diffuse from a region of high to low concentration when the P and N sides touch. From the N to the P side, electron move and unite with the holes. Similarly to how electrons and holes merge at the junctions, hole move from the P to the N side. Repeating, from the N to the P sides, electrons move and unite with the holes. Similarly, similar to how electrons and holes merge at the junction, holes move from P to the N side. A depletion range is created as a result of the near junction area becoming depleted of the carriers and being charged. becoming charged. The current diffusion results from the diffusion of the current. The charge creates an electric field in the depletion region. At the depletion area, the electric field causes a flow of minority carriers. This created current is known as the drift current, and this is referred to as drift. The directions of the diffusion and diffraction, the direction of the diffusion and the drift current are reversed. Directions of diffusion and drift current are reversed. Now, this is the second one. You have to explain with the help of circuit diagram working of junction diode as a full wave rectifier. Let's make that. This is the working of full wave rectifier. The two halves of each input AC input are used by the full wave rectifier. The diode provides low resistance. The diode provides low resistance when the PN junction is forward biased and biased, and high resistance when it's reverse biased. The circuit is set up so that if the diode for the is forward biased during the first half cycle, it will switch to the reverse bias during the second half cycle, and so on. Now the property, the characteristic property of the junction diode that makes it suitable for rectification. If this property, let's discuss that property. If alternating voltages is applied across a junction diode, then the current will flow only when the diode is forward biased. If alternating voltages applied across a junction diode, then the current will flow only when the diode is forward biased. This property of the junction diode can be used to rectify alternating current. The circuit used for this purpose is called rectifier. So this is your A and B part of the question 32. Hope you are clear with this. Let's move to the next question. Question 33. It contains A and B part again. So A part, first question, draw a ray diagram to show the working of the compound microscope. Obtain the expression for the total magnification for the final image to be formed at the near end. So this one is a required ray diagram to show the working of the compound microscope. This one. You can read it from here. Now the second part of it, you have to obtain the expression for the total magnification for the final image to be formed at the near point. So required expression for total magnification, first of all, magnification due to objective. This is MO is equal to H dash upon L, that is equal to L upon F naught. Also the magnification due to eyepiece. When the final image is formed at the near point, when final image is formed at the near point, this is ME is equal to 1 plus D upon FE. Now the total magnification is given by the product of both. So this is equal to L upon F naught 1 plus T upon FE. This is the answer to the question. So we are done till here in the second part. In a compound microscope, an object is placed at a distance of 1.5 centimeter from the objective of the focal length 1.25 centimeter. If eyepiece has a focal length of 5 centimeter and the final image is formed at the near point, find the magnifying power of the microscope. Okay, so to answer the question, let's go over here. This is the second part. Estimation of magnifying power. You are given U naught 1.5 centimeter, F naught is 1.25 centimeter. We have 1 upon F naught is equal to 1 upon V naught upon minus 1 upon U naught. So 1 upon 1.25 is equal to 1 upon V naught minus 1.5, or here you will have 1 upon V naught is equal to 1 upon 1.25 plus 1 upon minus 1.5. This is equal to this. So on solving this, you will get the V naught is equal to 7.5 centimeter. So the magnification is given by V naught, U naught, 1 plus D upon FE. Let's fill in the values. You have this as 7.5. This is equal to minus 1.5. 1 plus D is 25. FE is 5. So this is equal to minus 75 upon 10. 10 upon 15 multiply 6. This cancels. You have minus 30. This is the magnifying part. Minus 30. This is the answer to the question. Second part of the question. Minus 30. Hope you're clear with this. Now let's move to the B part of the question. Over here, you have to draw a ray diagram for the formation of an image of an object by an astronomical telescope in normal adjustment. Obtain the expression for its magnifying power. Let's go do this. So this is the required ray diagram for the formation of the image by an astronomical telescope in normal adjustment. So let's see over here in this particular graph, this graph depicts an astronomical telescope that is used to give angular magnification of distant objects. Angular magnification of distant objects. It has an objective lens with a large diameter and a long focal length. The eyepiece diameter and the focal length are both less than those of the objective lens. An actual image is created in the tube as its second focal point when light from the distant object enters the objective. This image is enlarged by the eyepiece, resulting in the final inverted image. The distance between the objective and the eyepiece, referred to as tube length, is the total of the focal length of the two lenses. Focal length of two lenses so that their innermost points coincide with each other. Now, let's say beta over here. Let's say the beta that the picture subtend at over here. This is this beta. This will be the angle that the picture subtends at the eye compared to the angle alpha that the object subtend at the lens. This one. So this magnifying power over here will be given by magnifying power M is equal to beta upon alpha. Beta is equal to H upon Fe. Here beta can be taken as tangent of beta and alpha can be taken as tangent of alpha because alpha and beta are very small. Okay, so beta is equal to tangent beta, that's equal to H upon Fe. Here H is the image height and this is focal length of eyepiece. So similarly, alpha, that's equal to tangent of alpha, and that is equal to h upon f naught. Here, this is again your, okay, not this is image, this is, in this case, this is objective. No, sorry, h is same. This f naught is your objective length, focal length, right? So m, that was equal to alpha upon beta, that is equal to actually tangent alpha upon tangent beta. This can be written as h upon fe divided by h upon f naught, that is equal to f naught upon fe. So this is the derivation for the formula. Over here, you have to derive an expression for the magnifying power. Magnifying power is given by f naught upon fe, where f naught is the local focal length of the eyepiece, and the fe, f naught is the focal length of the objective lens, and fe is the focal length of the eyepiece. Hope you're clear with this. Now the second part. The magnifying power of an astronomical telescope in normal adjustment is 2.9. Objective and the eyepiece are separated by a distance of 150 centimeters. Find the focal lengths of the two lenses. Okay. So second part here, D is equal to 150 centimeters. M is equal to 2.9. You have to find out F naught. You know, this is equal to F naught upon Fe. We just derived this, right? Also, D is equal to sum of F naught plus Fe. And from here, you have 2.9 is equal to F naught upon Fe. Or here you have D as 150. This is equal to F naught plus Fe. So from here, you have 2.9 into Fe is equal to F naught. So let's use this equation and fill it over here. So you have 150 is equal to 2.9 Fe plus Fe. This is equal to 3.9 Fe. That is 150. So 150 upon 3.9, that's equal to Fe. So on solving this, you will get the value of Fe as 38.46 centimeters. And you have to find out F naught. F naught is equal to 2.9 into 38.46. That is equal to 111.54 centimeters. So this is the answer to the question. 111.54 centimeters. Hope you're clear with this. Let's move to the next question, number E. 34. So here you are starting with section E. Some more typical questions will be following now. It says a lens is a transparent optical medium bounded by two surfaces, at least one of which should be spherical. Considering image formation by a single spherical surface successively at the two surfaces of a lens, Lensmaker's formula is obtained. It is useful to design lenses of the desired focal length using surfaces of suitable radii of curvature. This formula helps us obtain a relation between U, V, F for a lens. Lenses form images of objects and they are used in a number of optical devices, for example, microscopes and telescopes. So now, number one, an object AB is kept in front of the composite convex lens as shown in the figure. Will the lens produce an image? If not, explain. Okay. See, first thing, your lens is made up of two refractive index, that is N1 and N2. Refractive index N1 and N2, so it will not produce one image, it will produce two images. Two images will be produced because refractive index tends to bending of light. So here are two refractive indexes, hence it will bend the light in two directions. So two separated image will be formed. Hope you are clear with this. Second part, a real image of an object formed by the convex lens is observed on a screen. If the screen is removed, will the object still be formed? Explain. Yes, the real image is still located at the same point in space like an object, but each point on this object will now radiate light into a cone. So if your eyes not in those cones, you would not perceive it. But real image will be there. Hope you are clear? So third part. A double convex lens is made up of glass of refractive index 1.55 with both faces of the same radius of curvature. You have to find the radius of curvature required if the focal length is 20 centimeters. So here you have, we know 1 upon f is equal to mu minus 1 upon r1 minus 1 upon r2. We have focal length as 20 centimeters, mu is 1.55, r1 is equal to, let's say, r, so r2 is equal to minus r. Now let's fill everything in this equation. You have 1 upon 20 is equal to 1.55 minus 1 upon r minus of 1 upon minus r. So this makes 1 upon 20 is equal to 0.55, and this will be 1 upon r plus 1 upon r, that will be 2 upon r. So here you will have r is equal to 1 upon, no, it will be 55 upon 100 multiplied 2 multiplied 20. So this will cut at 11. So r is equal to 22 centimeters. Hope you're clear with this. Let's move to the B part. Again, or that means there is a choice in the question. It says two convex lenses A and B of focal length 15 and 10 centimeter respectively are placed coaxially D distance apart. A point object is kept at a distance of 30 centimeter in front of lens A. You have to find the value of D such that the rays emerging from lens B are parallel to its principal axis. All right. So, see, condition for the emergent beam to remain parallel after refraction through both the lens in terms of their foci is, see, that is the foci of both lenses should coincide. We have 1 upon f is equal to 1 upon f1, 1 upon f2 minus d upon f1, f2. As ray emerging from lens B, one parallel to its principal, therefore the object is, according to question, object is kept at focus. That means f is equal to u is equal to minus 30 centimeters. So this will be, now this equation will become 1 upon minus 30 is equal to 1 upon 15, 1 upon 10, d upon 15 upon 10. So you have a d upon 150 is equal to 1, this, 1 upon this, minus this will be plus this. So LCM 30, you have 2, 3, 1, d upon 150. This will cancel this. So this d will be equal to 30 centimeters. So d should be equal to 30 centimeters. Hope you're clear with this. So let's move to the last question of the paper, question number 35. A capacitor is a system of two conductors separated by an insulator. Two conductors have equal and opposite charges with the potential difference between them. The capacitance of the capacitor depends on the geometrical configuration, that is shape, size, separation of the system, and also on the nature of the insulator separating the two conductors. They are used to store charges like resistors. Capacitors can be arranged in series or parallel or a combination of both to obtain the desired value of capacitance. Now, what the question is, it's asking, number one, find the equivalent capacitance between the points A and B in the given figure. So that's easy. See, you have to just simplify this one. The first part, the given circuit, it can be redrawn like this was your point A. And here you have a capacitor C1. Here you have C2. This is C3. And C4, C5, and there was the point B. Further, here was one more. This is your C6 capacitor. Okay, now this is the, let's check. You have to find the equivalent capacitance. All right. So from here, you have C1 upon C2 is equal to C3 upon C4. That is equal to, let's say, C upon C or 1 upon 1. All C can be neglected. See, here was C1, C2, C3, C4. They were all equivalent to C. So that is why it is C upon C. Now all C's can be neglected so that the equivalent capacitance will be equal to 1 into 1 upon 1 plus 1, 1 into 1, 1 plus 1, comma 1 C. And this will give me, sorry, plus. Okay. So this will be equal to 1 by 2, 1 by 2 plus 1 C. This will be equal to 2 C. So this is the net equivalent capacitance, 2 C. Hope you're clear. The second part, a dielectric slab is inserted between the plates of the parallel plate capacitor. The electric field between the plates decreases. You have to explain this why. See, the total charge of the capacitor remains conserved on introducing a dielectric slab. Also, the capacitance of the capacitor increases to K times of its original value. So do remember this thing. Let's write it down. This is the second part. Total charge of capacitors remain conserved on introducing dielectric slab. Also, capacitance increases. Capacitance of the constructor, a conductor increases to K times of its original value. So that means CV is equal to C dash V, where C dash is equal to K times the original value into V. So since you have Q is equal to Q dash, so V will be equal to, V upon K. Now the electric field. So here you can say, V dash. So V dash is, wait. This is equal to, this is equal to V dash. So V dash is equal to V upon K. Now, electric field is given by electric field E is given by V upon D. This is equal to V upon K upon D. So this is equal to V upon D into this, or this is nothing but E upon K. So on introducing dielectric medium, on introducing dielectric medium, electric field reduces by 1 upon K times of its original value. So we are clear with this? It reduces 1 by K times of its original value. Hope you're clear with this. Now let's move to the third part of the question. It says a capacitor A of capacitance C, a capacitor A of capacitance C having charge Q is connected across another uncharged capacitor B of capacitance 2C. You have to find the expression for the potential difference across the combination and the charge loss by the capacitor A. All right, so let's go. So here, first thing, the initial charge on the capacitor is initial charge on the capacitor, that is Q is equal to C into V. This capacitor gets connected to another in parallel. So total capacitance, this capacitor is connected in parallel. So the total capacitance will be given by C plus 2C, that is equal to 3C. Right. So you have VC, potential difference across this combination. This is potential difference across this combination is given by VC is equal to Q upon C dash, that is equal to Q upon 3C. As both the capacitors are connected in parallel, therefore the voltage of both will be same. Let's write down as both are connected in parallel, therefore voltage of both will be same. Hope you're clear with this. Now let's move to the B part of the question. Or okay, this is wait, okay, fine. This is the one. The charge lost by the capacitor A. See, the charges on both the capacitors will be given by, I'm writing it over here. On the first capacitor, the charge is equal to CVC, that is equal to C into Q upon 3C, which is equal to Q upon 3. Also, the charge on the second, that is QB, is equal to 2C into VC. This is equal to 2C into Q upon 3C, or this is equal to 2 by 3 Q. So the charge lost by the capacitor A is charge lost by capacitor A. From both of them, this is equal to 1 by 3 Q. So this is the answer to the second part of the question. 1 by 3 Q. Hope you're clear? Now let's move to the second or option. Two slabs of the dielectric constants 2K and K fill the space between the plates of a parallel plate capacitor of plate area A and the plate separation D as shown in the figure. You have to find an expression of capacitance of the system. See over here. Okay, fine. So this is D by 3 and this is 2D by 3. Over here, this is 2K and K. Fine. Effective capacitance in series is capacitance. In series is given by C is equal to K E naught A upon D, or C is equal to C1 into C2 upon C1 plus C2. C1 is equal to 2K E naught A upon D by 3 from here. And C2 is equal to K E naught into A upon 2D by 3 from here. Right. So the C is equal to this. Let's fill in both the values in the given equation. So you will have C is equal to 2K E naught A upon D by 3 multiply by, this will be 3 by 2 K E naught A upon D. Yeah. One thing I will do, I will keep this 3 here. Hope you are clear? Let's rewrite this thing again. Wait. So this is 2K E naught into A into 3 upon D multiply by 3 by 2 K E naught A upon D. Whole thing divided by C1 plus C2. So this will be K E naught A. I'm taking this as common D. Here will be 6 and here will be 3 by 2. Now this will give me, let's do all the cancellations and everything. This will be like this, and this will cancel. D will cancel like with this D, and this 2 cancels with this. You have 9 into K into E naught into A upon D. This is divided by, this will be 15 by 2. So 2 will be taken up and 15 will be taken here. This will be 3 and this will be 5. So this is equal to 6 by 5 into K E naught A upon D. Yeah, so this is the right answer to the question. This is the 6 by 5. Let's write it down. 6 by 5 K E naught A upon D. This is the right answer to the question. And students, with that, we have completed all the questions of this paper, all the 35 questions, physics questions of this set 1 paper. And don't forget to visit our website, www.examsnet.com. This is a great place for you to practice your entrance exam question papers. Also, you must download our app. The link is available in the description box. So students, keep shining, keep rising high. That's all for this paper. A very best of luck for your exams. Bye. Hey, friends of Examsnet. Welcome to the question series of Examsnet. Students, you must have explored our website www.examsnet.com. This is a great place for you to practice your entrance exam question papers because all the PDFs of all the entrance exam question papers are available there. Also, you may download our app. The link is available in the description box for the better preparation of your exams. Students, today we will be solving CBSE class 12 2023 Delhi set 2 physics paper. Set 1 has already been uploaded, and this set 2, this particular video is in continuation with the set 1 only. All the questions have been discussed in set 1. Apart from the set 1 questions, the rest of the questions which are in set 2 are being discussed in this particular video. So let's start with the first question of the paper. A very best of luck. Here we go. It says a charge Q is placed in the center of a cube. The electric flux through one of its surfaces. See, assuming the cube as Gaussian surface, total flux will be given by total flux passing through the cube of length L, flux through cube of length L is given by flux is Q upon, but this is permittivity of vacuum. And this is charge. So the flux is given by this. Now you have been asked in the question electric flux through one of its surface. As it is having 6 faces, so the charge is symmetrically placed to each of the cube. Thus electric flux through each surface is equal. Each surface is having equal charge. Because the charge is placed symmetrically. It is placed in the center, so it is placed symmetrically. So flux through each face is given by, let's say, phi dash is equal to total flux divided by 6. So this is equal to Q upon 6 E naught. So this makes option B to be the correct answer. Hope you got that. Next is question number 2. Choose the correct option related to wavelengths lambda for the different parts of the electromagnetic waves. So you know that electromagnetic waves, they have a different spectrum. Question number 2, choose the correct option related to wavelengths lambda of the different parts of the electromagnetic spectrum. You know, the electromagnetic spectrum is divided into different waves. First, you have the radio waves, then the microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. Okay, so these are all the rays, microwaves, infrared rays, visible rays, ultraviolet rays. So all these are rays. Okay, now see, we are talking about the wavelength of it. Starting from the radio waves, the wavelength is the maximum. It goes something like this, keeps on, it's not, wait. They keep on, it's something like it diminishes a bit over here. Okay, so basically what I want to tell you over here is that the radio waves, they are having the highest wavelength, which keeps on decreasing in this direction, and the gamma rays have the least wavelength over here. So that makes, first of all, you are having X-rays, which are all mentioned. You have X-rays, you have microwaves, radio waves, and visible waves. So my radio waves, they have the maximum wavelength. Radio waves, they have the maximum, then are followed by the microwaves, then our infrared rays, and then our visible rays, then is your UV rays, then is your X-rays, and the wavelength, and the least one is for the gamma rays. Okay, so looking at that, which is the correct option to the answer, we have C option. This is the right one. Hope you got that. Next is question number 3. Figure shows a plot of stopping potential V naught versus 1 upon lambda is the wavelength of the radiation causing photoelectric emission from a surface. The slope of the line is equal to. See, whenever you know that frequency is equal to 1 upon lambda, your wavelength frequency is inversely proportional to the wavelength. So the photoelectric effect in terms of photoelectric effect in terms of stopping potential is given by plus EV, or V is equal to HV Question number 3, figure shows the plot of stopping potential V naught versus 1 upon lambda, where lambda is the wavelength of the radiation causing photoelectric emission from a surface. The slope of the line is equal to. You know one thing, that frequency is inversely proportional to the wavelength, and photoelectric effect in terms of photoelectric effect in terms of stopping potential is given by H mu is equal to, this is equal to H is plus EV. So you have V is given by the difference between the two, H mu minus H mu naught upon E. And if I compare it with the general equation of the line, Y is equal to mx plus C, you have M is equal to H upon E. So this is what you needed to find out, the slope of the line. So this is equal to H upon E. This is the answer to the question. Hope you understood. Next is question number 4. An ideal inductor is connected across an AC voltage. The current in the circuit is ahead of the voltage by phase, in phase by pi, lags voltage in phase by pi, is ahead of voltage in phase by pi by 2, or lags voltage in phase by pi by 2. See, you know the one thing, that E is equal to E naught sine omega t, and also this is equal to minus L. This is the real inductor, so minus L into di, that is change in current with respect to time. So from these both equations, you have E naught sine omega t is equal to minus L di upon dt. So you have di upon dt is equal to E naught. See, this is just showing the direction. So I'm considering the magnitude now. I will ignore the direction for the time being. So the magnitude, this will be E naught upon L into sine omega t. Let's integrate on both the sides. So you will have on integrating both sides, you will have I is equal to integral of E naught upon L sine omega t dt, or I is equal to E naught upon L minus 1 upon omega cos omega t, or this is equal to minus I'll take outside E naught L omega cos omega t. And you know, cos can be, if I want to convert that into sine, this will be sine pi by 2 minus omega t. So this is equal to, let's get this minus sign inside. So you will have E naught upon L into omega sine omega t minus pi by 2. This is your, this is multiply. This was your current. So I is equal to, this is equal to I naught sine omega t minus pi by 2. Therefore, the current lags voltage in phase pi by 2. So you have the option. This is the right answer to the question. Hope you understood this. Let's move to the next question, number 5. Assertion says, and in insulators, the forbidden gap is very large. And the reason is the valence electrons in an atom of an insulator is very highly bound to the nucleus. See, I think, yeah, both are correct. And the reason is the correct explanation for the assertion. See, an insulator is a material that has a very large band gap. Insulators have large band gaps or a very large energy difference between the valence and the large energy difference between valence and conduction band. This large energy difference makes it difficult for the electrons to move out of the conduction band where they can flow and create the electrical current, which means electrons are very tightly bonded. So that makes option A to be the right answer because both assertion and the reason are correct, and reason is the correct explanation to the assertion. Hope you are clear with this. Next is question number 6. Identify the electromagnetic radiation and write its wavelength range, which is used to kill germs in water purifier. Name the two sources of these radiations. So the entire range of the electromagnetic spectrum is divided into the rays, which are given over here. You have the radio waves, microwaves, infrared, near infrared, visible, ultraviolet, X-rays, and the gamma rays. This table shows their frequency and the wavelength, like how they are increasing and decreasing. Using this table, according to the question, UV radiations, they are used to kill germs in water purifier. Sunlight is the greatest source of it. Sunlight is the greatest source of the UV radiation. Man-made ultraviolet sources include several type of UV lamps, arc welding, UV lamps, arc welding, mercury vapor length, mercury vapor lamps. There are some devices emitting UV radiation, such as which is carbon, xenon, and the other arcs. So UV radiation, that is the right answer to the question. Hope you understood that. Yeah, name the sources of the radiations. We have discussed everything. So let's move to the next question, number 7. An electric dipole of dipole moment P is kept in a uniform electric field E. Show graphically the variation of torque acting on the dipole tau with its orientation theta in the field. Find the orientation in which the torque is 0 and maximum. The graph shows the variation of the torque acting on the dipole with the orientation theta in the field. The orientation in which the torque, now we have to find out the orientation in which the torque is 0 or maximum. I hope you are clear with this. So see, it is 0 over, it is maximum over here. The torque is maximum at this point and at 90 from here. Now, you are given the dipole is P. Dipole moment is P vector. And electric field, uniform electric field is E. So torque is given by, this is the cross product of both the vectors. So this is, now this torque depends on the orientation of the dipole, as this torque is given by this. So the magnitude of this torque is equal to P E sine theta. Right. So torque depends on the orientation of the dipole as this. Now you want to find out the orientation in which the torque is maximum. See, over here you are having, this is the direction of your electric field, and here is your charge flowing. So it has moved from here. Here I'm taking theta as 0. So this is the first case when theta is taken as 0. So that means sine theta 0 degree, sine theta will be equal to sine 0 degree, which is equal to 0. So in that case, torque will be 0, that is minimum. And then on the second case, when it is, this is the direction of the electric field, and here the charge is flowing from the minus q. From here, this is flowing in the upward direction, plus q. So this is your 90-degree angle in that case. So theta is equal to 90 degrees, sine theta is equal sine 90 degree. So that is equal to 1. The torque will be equal to PE. So this is maximum. Hence you found out, like, it will be minimum, it will be 0 in the case when the angle between them is 0, and it will be maximum when the angle between them is 90 degree. Hope you're clear with this. Let's move to the next question. A potential difference V is applied across a conductor of length L, cross-sectional area A. How will the drift velocity of the electrons and the current density be affected if another identical conductor of the same material were connected in series with the first conductor? You have to justify your answer. Okay. We know one thing, that the drift velocity is given by drift velocity, let's say Vd, is given by E upon M into tau. So this can be written as E into V M upon L tau. Current density is given by total current upon area. If another conductor of same length will be connected in series, it will remain the same and the potential will become half. Let's write it over here. So if another conductor of same length is connected in series, same length L is connected in series, in that case, current will remain same and potential will be half. So drift velocity will be half, will become half of the original one, like Vd dash will be equal to half of Vd, and this current density, it will remain the same because this is independent of the L. So hope you understood this. Let's move to the next question, number 9. A current of 1 ampere flows through a coil when it is connected to a DC battery of 100 volts. If DC battery is replaced by an AC source of 100 volts and the angular frequency is this, the current reduces to 0.5 amperes. Now you have to find the impedance of the circuit first thing. So let's write down, you have the DC current as 1 ampere, voltage is 100 volt, omega is equal to 100 radians per second. So IDC is equal to V upon R, or this is equal to 100 upon R. And you have this as 1, so that makes you R is equal to 100 ohm. Now, the AC is flowing. It is said that that is replaced by an AC. So now the AC current is 0.5 ampere. So it is something like this. This R is connected to L, and like this. So this is the positive and the negative. This is a 100 volt battery. Now, impedance, the first thing. Impedance of the circuit, this is what you need to find out. Impedance is given by Z is equal to root of R square plus omega L whole square. So this is equal to R. We just calculated, it is equal to 100. See, one more thing. When AC is applied, you have impedance as V upon R. So now let's make it very easy. V is 100, I is 0.5. That makes it 200 ohms. Hope you understood this. Now the second one that you have to find out the self-inductance of the coil. Second part, self-inductance of the coil. We know that Z square is equal to R square plus XL square, or you have XL square is equal to Z square minus R square. Z we just solved, this is equal to 200 and R was 100. That makes 40,000 minus 10,000. That is equal to 30,000. XL, this is 30,000. XL square. So XL will be the root of 30,000, which on solution will give you 173.21 ohms. Now, XL is equal to omega L, or this is omega into L, or L is equal to XL upon omega. So this was equal to 173.21 and omega is equal to 100. That makes it 1.7321 H. So this is the answer to the second part. Self-inductance 1.73 H. Given that angular frequency is equal to 100 radians per second. So that's why the omega has been substituted as 100. Okay. Now the third part of the question. The phase difference between the voltage and the current. Let that be phi. Let that be denoted by the angle phi. So you know for the third part that cos phi is equal to R upon L. So R was 100 and L was 1.73. So cos phi will be equal to 57.73. Phi will be equal to cos inverse of 57.73. This is the right answer to the question. This is cos inverse 57.73. This is the right answer to the question. Hope you understood this. Let's move to the next question then. Then the primary coil having NP turns of an ideal transformer is supplied with an alternating voltage VP, which is over here. Obtain an expression for the voltage Vs induced in its secondary coil and S turns. Mention two main sources of power loss in the real transformers. Okay, so this is having the number of turns NP and this is having the number of turns as NS. For a simple transformer, which is shown over here, this is transformer symbol. The simple transformer, which is shown in the figure, the output voltage Vs, output voltage, is almost entirely dependent on the input voltage Vp, input voltage, and the ratio of the number of loops of the primary and the secondary coils. Faraday's law of induction for the secondary coil gives its induced output Vs as according to Faraday's law of induction for the secondary coil gives its induced output voltage Vs as minus Ns d phi upon dt. All right. Now here, you know, this is, let's say, equation 1. This is the number of loops in secondary coil. Change in flux with respect to time. Change in magnetic flux. And the cross-sectional area of the coil is same on either side as the magnetic field strength. So let's write down the cross-sectional area of the coils is same on either side, as is the area of the coils is same on either side as is magnetic strength, magnetic field strength. So delta phi upon delta t is also same on both the sides. So the input primary voltage Vp is related to, so input primary voltage Vp is equal to minus Np change in flux upon time. Let's say this is equation 2. Now, Lenz's law tells us that primary coil opposes the change in flux caused by the input voltage. Remember this. Snell's law tells us that primary coil opposes the change in flux created by the input voltage Vp, hence the minus sign is given over here. Okay. Now, dividing both the equations, this was number 2 and this was number 1, dividing both the equations. Dividing 1 and 2. You have Vs upon Vp is equal to Ns upon Np, or you have Vs is equal to Vp and S upon Np. Hope we are clear with this. Now, the last part of the question mention we have obtained an expression for Vs. We have derived that expression. So we got Vs is equal to Vp into Ns upon Np. Right. Now the second part. You have to mention two main sources of power loss in the real transformers. So two main causes of energy loss. This is number 1, heat loss due to copper. It is the heat energy loss across the resistance of the copper winding used in the primary and the secondary coil. Number 2, hysteresis loss. Hysteresis loss. This loss is because of the heating of the core, heating of the core due to its repeated cycles of magnetization and demagnetization when an alternating EMF is applied across the primary coil. Hope you're clear with both of these, right? So this is the answer to the question. Hope you're clear with this. Let's move to the next question, number 11. It says, write the limitations of the Rutherford's model of atom. This is a theoretical question. You must be aware of it. Quite an important one, actually. Okay, the second one, before moving, this is a lengthy question. It's having a choice, A and B part. A is already divided in 2 parts. B is also divided in 2 parts. So let's start with A part first. A question, first part. You have to discuss the limitations of the Rutherford model. I told you it's an important one. I hope you already know the answer. See, this model failed to explain the stability of atom. Failed to explain the main thing, stability of the atoms. Number 2, the arrangement of the electrons in a circular path was not defined. Arrangement of electrons in a circular path was not defined. Then any particle that is moving in a circular path will undergo acceleration and radiates energy. Thus, the revolving electron would lose energy and finally fall into the nucleus. So everything will collapse, right? I'll draw it like this was the first and the second and the third one. So any particle which is moving in a circular orbit, it will occupy some acceleration and it will radiate energy. Thus, revolving electron will ultimately fall into the nucleus. So everything will collapse. Okay. Now, the second part, it says this is the A part, limitations of the Rutherford model. So the second one, the wavelength of the second line of the Balmer series in hydrogen spectrum is 4861 angstrom. Calculate the wavelength of the first line of the same series. For the first line, I'm gonna erase this. So A question, second part. So for the first line in the Baldwin series, you have 1 upon lambda is equal to, okay, this is for, wait, A question, second part. For first line of, first line in Baldwin series, you have 1 upon lambda is equal to 1 up r into 1 upon 2 square minus 1 upon 3 square. This will give you this. So r 5 upon 36. So this is equal to 5r upon 36. Okay. Now this is for the first line. For the second line, for second line in the given series. You have 1 upon, you are given in the question 1 upon 4861 is equal to 1 upon 2 square minus 1 upon 4 square. This is equal to r 1 by 4, 1 by 16, r 16, this is 12 upon this, or this is equal to 3 by 4, 3r by 4. Let's say this is first and this is second equation. Now dividing both of them, dividing equation 2 by equation 1, you have lambda upon 4861 is equal to 3r upon 16 multiply 36 upon 5r, or you have lambda is equal to 4861. Yeah, on solving this, you will have 27 upon 20. And this whole thing will give you 6562 angstrom. Hope you are clear with this. So the answer, the second part is 6562 angstrom. Hope you are clear with this. So now let's move to the second part of the question, B part. It says increase in the intensity of the radiation causes photoelectric emission from the surface, does not affect the maximum kinetic energy of the photoelectrons. You have to explain this. I'm repeating the question. Increase in the intensity of the radiation causing photoelectric emission doesn't affect the maximum kinetic energy. You have to explain this. See, on increasing, I'm clearing the screen again. So on increasing the intensity of incident light, the current in the photoelectric cell will increase. Current in photoelectric cell will also increase. The energy of the photons, which is h mu, will however not increase with the increase in, no increase with the increase in the this intensity, and has the kinetic energy of the, if see this is not increasing, kinetic energy of the photo of the emitted electrons will also not increase. Hope we are clear with this. Now the second part, the photon emitted during de-excitation from the first excited level to the ground state of the hydrogen atom is used to irradiate, it is radiate a photocathode in which stopping potential is 5 volt. Calculate the work function at the cathode used. See the second part. The photo in photoelectric effect, stopping potential is directly proportional to the maximum kinetic energy of the emitted electron. This maximum kinetic energy is further dependent on the frequency of the incident light, as well as it is further dependent on frequency of incident light as well as the work function of the cathode. Combining these two facts, we can arrive that the work function of the cathode used ठीक है. All right, so work function of the cathode is used, so kinetic energy is equal to this minus this, or this is equal to the difference between where h mu is the difference of the E2 and E1. Hope you are clear with this. Let's move to the next question. Okay, this is the last question of the paper. Hope you are clear with this, and students, with that, don't forget to visit our website www.examsnet.com. Here you will find so many entrance exam question papers along with the detailed PDF solutions. Also, you may download our app. The link is available in the description box. So students, keep shining, keep rising high. That's all for this paper. And don't forget to watch set 1 and set 3 paper as well. Bye. Hey, Shams of Examsnet. Welcome to the question series of Examsnet. Students, you must have explored our website www.examsnet.com. This site is a great place for you to practice your entrance exam question papers, because here you will find all the papers along with their detailed PDF solutions. For a better preparation of your exams, must download our app. The link is available in the description box. So students, let's start with today's paper. I'll be solving CBSE Set Class 12 Delhi 2023 Set 3 paper. I'll be solving the physics part of the paper in this particular video. Set 1 and Set 2 have already been solved and uploaded, and the Set 3 is in continuation with those sets only. Hope you're clear with this. So now let's start with the very first question, a very best of luck. Section A, first question. Two horizontal, thin, long parallel wires separated by a distance r carry current I, each in the opposite direction. The net magnetic field at a point midway between them will be. Okay. See, I'll be using the thumb rule over here. According to this thumb rule, when you are using your right hand and the thumb points towards a current carrying direction, thumb points to current carrying direction. And then see, your fingers will roll. The fingers curl in the direction of the magnetic field around the current carrying conductor. Fingers, they will curl where? Into the direction of magnetic field around current carrying conductor. Okay. Thus, the magnetic field at the point due to which, due to the wire on the left is downwards. Again, applying the same theory to the right hand side wire. The magnetic field at the point due to that wire exists downwards. Hence, after summing the two magnetic fields, the net field will be zero only. So, first option is the correct one. Option A, this is the right answer. Hope you are clear with this. Next is question number 2. Which of the following cannot modify an external magnetic field as shown in the figure? So here you're having a figure, and you have to answer that which of the following cannot modify an external magnetic field over here. Like this magnetic field cannot be affected by which of these? The right answer to the question actually is silicon. That is the option. See, if I talk about nickel and the copper, nickel and copper, they have the ferromagnetic properties. Ferromagnetic properties. So they will affect the external magnetic field. Silicon is a weakly, this one is a weakly diamagnetic material. Diamagnetic material where susceptibility depends on doping and sodium chloride. This is diamagnetic in nature. Therefore, looking at this is weakly diamagnetic and this is diamagnetic. So silicon only will not modify the external magnetic field shown over here. Hope you are clear. Next is question number 3. E, C, and mu, they are energy, velocity, and frequency of a photon. Which of the following represents the wavelength? That's an easy one. Energy of the photon is given by h mu, or this is equal to h into c upon lambda, or lambda is equal to h c upon e. That makes option C as the correct answer. Hope you understood this. Next is question number 4. The energy required by an electron to jump the forbidden band in silicon at room temperature is how much? See, the forbidden gap or the band gap for the purer silicon is, let's write down, band gap or forbidden gap for pure silicon. It's 1.1 electron volt. So this much energy is required for an electron to jump the forbidden band in silicon at the room temperature. That makes D option to be the right answer. Hope you understood this. Next is question number 5. What is the ratio of inductive and capacitive reactance in a circuit? Okay, first thing, you're talking about inductive and capacitive reactance. So inductive reactance, that's XL is equal to angular frequency multiplied by L, conductance, inductance. So now the capacitive reactance is XC is equal to 1 upon omega C, and yeah, dividing both of them. Let's do dividing both of them. XL upon XC is equal to this upon 1 upon this. This will be equal to omega square L into C. That is your first option. Hope you are clear with this. Next is question number 6. In an interference experiment, third bright fringe is obtained at a point on the screen with a light of 700 nanometers. What should be the wavelength of the light source in order to obtain the fifth bright fringe at the same point? Okay. Before discussing the answer, the position of the nth bright fringe is given by position of nth bright fringe. This is given by yn is equal to n into lambda into d upon the small d. So you are given over here something that this lambda is 700 nanometers. So y3 will be equal to 3 into 700 into d upon small d, or y3 is 2100. This. The fifth bright fringe due to the light of wavelength lambda. Now, fifth bright fringe due to light of wavelength lambda is formed at y3. So y5 is equal to y3. Y5 will be given by 5 into lambda dash into d upon d, and this is equal to 2100. This is nanometers into capital D upon small d, and they will cancel out. You will have lambda dash is equal to 2100 upon 5, or this is equal to 420 nanometers. So the right answer to the question, this is 420 nanometers. First option. Hope you are clear with this. Next is question number 7. Question number 7 says the given figure doesn't show a balanced wheat zone bridge. This is the assertion. And the reason is for a balanced bridge, small current should flow through the galvanometer. Looking at over here, first of all, I have to check that whether it is following the Wheatstone bridge or not. So let's go for that. This figure can be simplified by, like, here you having a 2 ohm resistance, let's say that's P, and here you have a 3 ohm resistor, let's say that is Q, and here mid you are having the galvanometer, this. Okay, so this is PQRS, and this is equal to 3 ohm, and this is 2 ohm. Now, for a balanced Wheatstone bridge, balanced Wheatstone bridge, you should have that P upon Q should be equal to R upon S. Let's write it over here. P upon Q should be equal to R upon S, or that's 2 upon 3 should be equal to 3 upon 2. Actually, they are not equal. So that's not a Wheatstone bridge. That means the assertion was correct. Okay. Let's move over here. That means this is right. This doesn't show a balanced Wheatstone bridge. Now the reason says for a balanced Wheatstone bridge, the small current should flow through the galvanometer. See, in the case of a balanced Wheatstone bridge, the current through the galvanometer must be equal to 0. That means this is wrong. It should not small around. It should be 0. So reason is correct. Sorry, assertion is correct, but the reason is wrong. That makes option C to be the correct answer. Hope you're clear with this. Let's move to the next question. Number 8. Plot a graph showing the variation of photoelectric current as a function of anode potential. This is photoelectric current over here, and this is your anode potential. For the two light beams having same frequency but different intensities I1 and I2, where I1 is greater than I2. Over here, you have I1 greater than I2. Now mention its important feature. See, we take the radiations of different frequency but of the same intensity. Different frequency, same intensity. For the higher frequency, photoelectric current becomes higher, and for the lower frequency, photoelectric current becomes lower. For higher frequency, photoelectric current, it becomes higher, and for the lower frequency, the photoelectric current becomes lower. But after a specific after a specific anode potential, photoelectric current for all the radiations having different frequencies remains constant. So here frequencies are constant for, at this point, both radiations. This is known as the saturation current. This is your saturation current. Hence, the saturation current is independent of the frequency of the radiation. Now, this was its important, one of the important features. Hope you are clear with this. Now, let's move to the next question, number 9. It says, how are electromagnetic waves produced? You have to write their two characteristics. This is a three-article question. So, lengthy one. I just explained that to you. See, the electromagnetic waves, they are the combination of electric and magnetic field waves produced by moving charges. The creation of all the electromagnetic waves begins with the charged particle only. Charged particle only. Yeah, so the creation of all electromagnetic waves, it begins with the charged particle. This charged particles creates an electric field which can exert a force on another nearby charged particle, right? Force on another charged particle. When it accelerates as a part of the oscillatory motion, the charged particle creates ripples and oscillations in the electric field. And it also produces a magnetic field as predicted by the Maxwell's equation. Magnetic field, Maxwell's, as predicted by the Maxwell's equation. Once in motion, the electric and the magnetic fields created by the charged particle are self-perpetuating. The time-dependent charges in one field, electric or magnetic, produce the other. Now, both electric and magnetic fields in the electromagnetic wave will fluctuate in time, one causing the another to change. Electromagnetic wave, that are the photons, they are produced anytime a charged particle experiences a change in the velocity. electromagnetic wave, that is your radiation that is produced when the charged particle changes its velocity, is how energy is conserved. This energy is your light. A simple example of this in the production of the microwaves. Inside a microwave oven, it is inside a microwave oven is a component which is called magnetron. So inside the racetrack of the electron, inside this magnetron is a cavity which is like a circular racetrack for the electrons. The electrons go round this circular track at immense speeds while they are running in their little circles. As they are having very high speeds. A fluctuating magnetic field causes the electrons to wiggle back and forth towards inside and outside of the racetrack. This wiggling happens at a very high frequency. And what causes a generation of microwaves? Now, the second part of the question, you have to write down the two characteristics of the electromagnetic waves. See, they are transverse. First one, they are transverse in nature. Characteristics, the second part. First, they are transverse in nature. Second, electromagnetic waves consisting of oscillating let's write it now. They consist of oscillating magnetic and oscillating magnetic and electric fields that are perpendicular to each other. Okay, so this is the answer to the question. Hope you are clear with this. Let's move to the next question. Then question number 10. 3-point charges q, small q minus q, they are kept at the vertices of an equilateral triangle of the side L as shown in the figure. Now first question, what is the electrostatic potential energy of the arrangement? See, the electrostatic potential energy of the arrangement is given by U is equal to 1 upon 4 pi E naught Q into minus Q divided by L plus minus Q into Q divided by L, and the last one Q into capital Q upon L. So this gives me 1 upon 4 pi E naught. Here will be, let's write them. I'm taking the L outside, okay? So this will be minus Q minus Q square plus Q into Q. This will cancel and this will be equal to minus Q square upon 4 pi E naught upon L. So this is the first answer to the question. Now the second one, the potential at the point D. This is the point. You have to find out the potential at this point. See, first of all, what is the length of QD? This is equal to, this is a right angle triangle. This is L by, this is a right angle triangle. This is L, this is L by 2. So QD will be given by root of L square minus L by 2 whole square. This is equal to L square minus L square upon 4. So this will be 4L square minus L square upon 4, or this will be equal to root 3 by 2 into L. That's it. You have the QD as, I will not, this is equal to this much. Right. Now you have to find out the potential at D. Let's go for this. I think I have it. Okay. Potential at the point D, that is VD, is equal to again 1.4 pi E naught. This will be, see the point, the charges here you are having minus Q, Q and Q. Okay, fine. So this will be given by minus Q upon L by 2 plus Q upon L by 2 plus capital this into this. Okay. So this is equal to 1 upon 4E. This, I'm taking the L outside. This will be equal to minus 2Q and L. Okay. They will cancel out, right? Plus 2Q. And here will be plus 2 upon root 3 q. Yes. So this will cancel and you will have this 2 and this 4 will also cancel. So 1 upon this 2 pi e naught into L and here will be root 3 also and here will be q. Let's write it properly. This is q upon 2 root 3 pi e naught L. This is the answer to the second part of the question. Hope you are clear with this. Let's move to the next question then. Question number 11, two identical circular loops P and Q, each of radius R carrying current I, are kept in a perpendicular plane such that they have a common center O as shown on over here in this figure. So you have to find the magnitude and the direction of the net magnetic field at the point O. See, you are having two coils, the P and Q. In P, current is in the anti-clockwise direction, as you can see from here. This is the direction of the current. This is the direction of the current over here. See. So the magnetic field BP will be the in the given direction like this. This will be the direction of BP. Similarly, in the coil Q, the direction of magnetic field BQ will be shown by using the Fleming's left hand rule. So this will be the direction of BQ. All right. So I hope you are clear with this. This is the direction of BP and this is the direction of BQ shown over here. Now, the net resultant of BP and BQ, let's say that is equal to B. This is the magnetic field B. This is at an angle of 45 degree. B will be given by, I'm applying, this is a vector line, right? So B will be equal to square root of BP square plus BQ square. Here both BP and the BQ, they are equal because the coil is having same current and same radius. Both coils have same current and same radius. So therefore BP is equal to BQ. That gives you root of 2 BP square. That is equal to B. Let's continue from here. So B will be given by root 2 into BP. Also, you know that BP is given by mu naught I upon 2R. So this will be equal to your B will be equal to root 2 into mu naught I upon 2R, or this is equal to mu naught I upon root 2 into R. So the net magnetic field is oriented to both the fields at, therefore, net magnetic field is oriented to both the fields at 45 degree. Question number 11, two identical circular loops P and Q, each of radius R carrying current I, are kept in perpendicular planes such that they have a common center O as shown in the figure like this. So these are the two coils P and Q, both are having, this is the direction of current in both of them. This is the direction of the current in P and Q respectively. So now, see, this is the direction of the current in P. So according to this, what will the direction of magnetic field? It will be given by this. This will be the direction of magnetic field and for the P coil, and this will be the direction of magnetic field for the Q coil. According to the Fleming's left hand rule, I'm using, so these are the two direction of the magnetic fields. You have to find out the net magnetic field, right? This is what you had to find out. So first thing, you have BP, this is equal to mu naught into Ni upon 2R. This is in J direction. This is in the J cap direction, and this is magnetic field due to the loop P. And for the loop Q, the magnetic field is given by mu naught into N into I upon 2R I cap. Right, only the directions are changed, rest the magnitude of both of them, they are equal. So the net magnetic field B net is given by the summation of 2 mu naught Ni upon 2R I cap plus this upon 2R J cap. So carrying it further, B net is given by, I'm taking mu naught n I upon 2r I plus j. So now it's magnitude. This is the vector. And this, of course, these are the vectors. Okay. So now the magnitude will be given by this. This magnitude is equal to mu naught n I. This is the constant. Let's take it outside. Root of I. These are the unit vectors. So I, like this magnitude is 1. Similarly for the j. So 1 square plus 1 square. This is equal to root 2 upon 2r into mu naught into n into I. Or this is equal to mu naught n I upon root 2 into r. Gives the magnitude. Now you have to find out also the direction. So direction, this will be given by, for the B net, direction for B net will be given by division of B net upon its magnitude. So this will be used to find out the direction. This is equal to mu naught n I upon 2r I plus j, and this is equal to mu naught n I upon root 2r. Um, this will cancel, and you will have mu naught, sorry, I cap j cap upon 2 into root 2. Right. So this root 2 and this will also cancel. So this is equal to I cap plus j cap upon root 2. Therefore, the direction, therefore, it will make an 45. So the direction of both of them will be 45-degree angle between them. So there will be direction of 45-degree with BP and BQ, right? That means this particular angle comes out to be 45-degree. Hope you are clear with this. Now let's move to the second part of the question. A long straight conductor kept along x dash x-axis carries a steady current I along the positive direction of x. At an instant t, particle of mass m charge q at the point xy moves with the velocity v and the positive direction of y. Find the magnitude and direction of force on the particle due to the conductor. Okay, so let's clear the screen. So here you have something like this. According to the question, it will look something like this. These are the three directions, X, Y, and Z. Right, this is your V and okay. Long string x-axis, long straight conductor kept along this. So here's the conductors. There is a steady current in this direction at an instant t. The particle moves. Fine. So mass of the particle is m, charge is q, and it moves with the velocity v along the positive direction. See, according to the Fleming's left-hand rule, first of all, from the relation, you have the force is given by QVP minus I K cross. So this is equal to QVP. This is the negative x-axis and the K. This will be giving me the J. The cross product of these two unit vectors, because these are three coordinate axes. So the cross product I and J will give me K. Now using the Fleming's left-hand rule, direction of the magnetic field will be using Fleming's left-hand rule. Left hand rule, direction of magnetic field will be inside the plane of the paper. Direction of magnetic field will be inside the plane of the paper. So the force will be in the direction of the motion of the conductor. So force will be in the direction of motion of conductor. Therefore, the direction of force will be in the positive y direction. Hope you are clear with this. Then let's move to the next question. Question number 12. Two conductors made of same material have equal lengths but different cross-sectional areas A1 and A2. A1 is greater than A2. They are connected in parallel across the cell. Show that the drift velocity of the electrons in the two conductors are equal. All right. So, see, when the two wires they are connected in parallel, potential difference across the wires will be same. You know that. Two wires in parallel means potential difference between them will be the same. Right. So that means V1 is equal to V2. So this is the potential difference for the wire A, and this one is for wire B. Since the two conductors, they are made up of same material, same length, their resistivity will be also same. That means rho 1 is equal to rho 2. Let's say that's equal to rho only. So that means the ratio of the resistance will be the same. Sorry, the ratio of the resistance will be equal to, because the resistance that's inversely proportional to area. So R2 upon R1 is equal to A2 upon A1. Let's say this is equation 1 and this is equation 2. Now current flowing through the conductor with the cross-sectional current I1 flowing through a conductor with cross sectional area A1 is given by I1 is equal to A1 into N into V into mu1. So also I2 will be equal to this. Let's divide both, add both of them since both conductors are in parallel, therefore are connected in parallel. So total current will be equal to I1 plus I2. I'll be using Ohm's law now. V is equal to IR. So that means I1, because the V is same, V1 is equal to V2. So I1 R1 is equal to I2 R2. Now, let's say this is equation 3. Now using 3, you have this is equal to A2 this. Right. So A1 into mu1 is equal to this. Okay. Yes, we already have seen that R2 upon, yes, from 2, this is equal to A1 upon A2. So what will happen? This is velocities, right? V1 is equal to V2. So the drift velocities of the electrons in the two conductors are equal. Drift velocity of electrons into conductors are equal. Hope you're clear with this. So that's it. Hope you're clear. Next is the question number 13. An alternating current I is equal to 14 sine pi 100 pi t. Sorry, I'm repeating the question. Alternating current I is equal to 14 sine 100 pi t. A passes through a series combination of the resistor 30 ohm and an inductor of 2 upon 5 pi. H taking root 2 as this, you have to calculate the RMS value of the voltage drops across the resistor and the inductor first. So let's start with the first question. Current is 14 sine 100 pi t A. So resistance here is equal to 30 ohm. L is equal to 2 upon 5 pi h. Yes. Yeah, these things are given over here. So now you have angular omega is equal to 100 pi. Yeah, from here. Okay. So XL is equal to, XL is equal to inductive resistance. This is your inductive reactance is omega into L. So this is equal to 100 pi into 2 upon 5 pi. This will be equal to 40 ohm. Now impedance R is equal to, Z is equal to R square plus XL whole square. So R just that was equal to 30 and XL is 40 whole square. This is equal to 900, 1600, that is 2500. So the root will give you 40 ohm. That is equal to Z, right? I think this is what you needed to find out. Okay, no, this is we just calculated the impedance and now I have to find out the RMS value of the voltage drop across the resistor and the inductance. All right. So now the first part. VRMS is equal to IRMS into Z. We know that IRMS is equal to I naught upon root 2. So this is equal to 14 and root 2 is given to you in the question as 1.4. So that is equal to 10 ampere. Therefore, VRMS will become 10 into 50, which is equal to 500 volt. So the voltage drop across the resistor, voltage drop across the resistor VR is equal to I RMS multiplied by R, that is equal to 300 volt. Right, and the voltage drop across inductor is VL is equal to R IRMS into this is XM. So this is 400 volt. So the right answer to the both the questions, for the resistor it is 300 volts and for the inductor it is 400 volts. Hope you're clear with this. The second part, you have to find out the power factor of the circuit. Okay, so the second part, power factor is cos of angle between them. See, if you are having this as the resistance and here is your XL, this is your Z, this is XL, right? So this is your power factor, that is cos of angle between them. So cos phi will be given by R upon Z. R was 30, Z was 50. So this is equal to 3.5, that is 0.6. So phi, cos phi, that is your power factor. Cos phi is equal to 0.6 or your power factor is equal to 0.6. This is the right answer to the question. Hope you are clear. Next is the last question for this paper. Calculate the binding energy of an alpha particle in MeV. You are given the mass of the proton, neutron, and helium nucleus as this. Okay, fine. So one U is given to you as 931 MeV upon C square. Let's write down, you have a mass of the proton as 1.007825 units, and neutron as 1.008665 U, and mass of alpha nucleus. See, this is nothing but your helium nucleus. This is nothing but your alpha particle. So this is 4.002800 U. Now the binding energy, this is given by the change in mc squared. So this is 2mp plus 2mn minus m alpha whole square. Right. So the change in mass, that is the Question number 14, calculate the binding energy of an alpha particle in MeV. Given mass of proton, neutron, and mass of helium nucleus as this much, 1U is taken as 931 MeV upon C square. Okay. You are given these three masses. So this is, let's say this is equal to MP, this is equal to Mn, and this is M alpha. And the binding energy is given by change in mass, that is your mass defect multiplied by C square. First of all, let's calculate the mass defect. This is given by, since it is followed by the two liberation of two protons, so 2 into MP plus 2 into neutrons minus this mass of the helium nucleus, that is equal to, let's say, M alpha. Okay, so this is equal to 2 into 1.007825 plus 2 into 1.008665 minus 4.002800 U. All right, so this gives you a total of, this will be equal to 0.03018 U. Now U was equal to 03018, U is equal to 931 MeV upon C squared. So this gives you a total of 28.09758 MeV upon C squared. Now let's get back to our binding energy. That was equal to delta M C square. So this is equal to 28.09758 MeV upon C square into C square. This will cancel. So the answer is 28.09758 MeV. So this is the answer to the first question. The answer here is equal to this. Okay. Now, the second one, a heavy nucleus P of mass number 240 and binding energy 7.6 MeV per nucleon splits into two nuclei X and R of mass number this and this. Binding energy per nucleon is given by this and this respectively. Calculate the energy released in the fission. Okay, so let's clear the screen. So now according to the question, you are having a heavy nucleus P, which is having the mass number as 240, and it splits into Q and R. Q is having the mass number 110, and this is having the mass number as 130. As per some energy is released. So as per the given data, energy released in the fission is energy released in the fission is given by, that is equal to 100 into 110 into 8.5 plus 130 into what is it? Yeah, 8.4 minus this 240 into 7.6 from here. So this is equal to, on solving, this will give you 203 MeV. So this is the energy released in the fission, and answer to the question is 203 MeV. So students, with that, we have completed all the questions of the set 3 of this paper, and don't forget to watch set 1 and set 2 papers also for this. So students, that's all for this paper, and don't forget to visit our website www.examsnet.com. Also, you may download our app. The link is available in the description box. So do visit our website and download our app for a better preparation of your exams. So students, keep shining, keep rising high. That's all for this paper. Good luck and bye.